So if somebody wants, so you're online also? Okay. So before we start, I covered the relationship of the degrees of freedom of any physical system with its computability, right? Its computation power. I hope that thing is clear. I mean, I connected that thing with the data logic. I connected that thing with the quantum computing. How many degrees of freedom are there, and how the entanglement in the quantum computing basically gives you an extra leverage. That extra leverage that normally is claimed. Other if the entanglement is not there, or a full entanglement is not there, accordingly the degree of or the power of computation power of the quantum algorithm is lesser. So it is not like that. It is always 2 raised to power n that is claimed normally. It basically depends if you cannot factor the state and you have the maximum degrees of freedom available in the representation. Only then you can apply, I mean, the operations on that and can get can leverage the maximum 2 raised to power n computational power of the quantum computing. So that point is very important. The entanglement and how the degree of entanglement, how, because that creates the degrees of freedom. So the degrees of freedom of the physical system is directly related to how fast or how efficient it is computing, right? And then we connected the same concept with the digital logic also, which saw that in digital logic, due to the discretization, the degrees of freedom are finite. Although they also increase with the power of 2 as you add more bits, but still, I mean, they are finite, and you can calculate how many particular kind of, see, we saw that for 2 qubit case, we saw that there are only 16 possible functions, and then so on. So accordingly, 2 raised to power 2 raised to power n, you can find how many functions are possible in a particular data domain. And then we connected the same degrees of freedom concept to finally to the feature space or the AI. In AI also, you also saw that as we decrease the we try to have the degrees of freedom as less as possible, which can justify your data. Basically, that is the aim in AI. You are trying to have a minimum degrees of freedom so that whatever your data space is, you effectively and efficiently capture it. So this degrees of freedom concept that is basically, I mean, in physics terms, is called the Hilbert space. I mean, yesterday we used the term Hilbert space, but actually it is nothing but the degrees of freedom, independent degrees of freedom, right? Orthogonal degrees of freedom, which we call the basis vectors. So same concept was there in the AI also. Basically, you want to arrive in the last layer of the AI, whatever the AI model is. In the last layer of the AI, you want to arrive at a particular Hilbert space at a minimal Hilbert space from which you can then perform your particular task. You sum that and you weigh and sum those features, last features, and you can perform whatever task you want to do. Say its classification, its regression. That is performed using the last Hilbert space that is available in the AI. So that is how we connect the AI with the Hilbert space, and through Hilbert space, the connection is apparently, we saw that apparently the connection also exists of the AI feature space with the qubits. So if you can have a mapping from that feature space to the qubits, you can directly utilize that advantage. That is how that is what we closed yesterday. So I mean, if you people who are present here, or I mean anybody who's online, he wants to have a question on that, we can, I mean, postpone. Once I complete this hardware lecture, I'll take the combined hardware and the yesterday's lectures questions. I tried to take yesterday also because, but I mean, it was second last lecture. Probably people were also kind of tired, so there was no questions. So I am still open to the questions. Whatever we covered yesterday, we can again, I mean, have the questions on that. So, but let's start today with the hardware part. Again, just like I told you that yesterday, the last lecture was kind of my, I mean, passion, because I have done the quantum machine learning, so I am interested to connect the quantum computing with the machine learning somehow. So I said that it is probably one of the topics that I passionately cover. Similarly, since my master's in quantum hardware, so again, I mean, you'd see that, I mean, this is the topic that I would love to talk about. So let's see. I mean, if I can I can make get you interested in that, into the hardware, quantum hardware, as well as invoke into enough interest so that I have questions at that. So we all are here basically because there's a hype. Quantum computing is making headlines. Otherwise, I mean, we would not have. How many participants online were there? Yesterday they showed probably 786, 784. I don't know how many today. Yesterday it was amazing. Somebody remarked that I am the 786th participant. I don't know whether it's true or not, but there was a remark in the question. It was amazing. For me, it was amazing that it can be possible. So anyway, uh, all these people who have got interested in this workshop and who have attended this workshop, who have joined us, are basically interested in it because quantum computing is making headlines, and this has been more visible since 2021. Once the IBM they first started and Google AI at the same moment, almost in parallel. They first open sourced their computer, or they came up with the frameworks, SDKs, allowing us to control their computers. And since then, there is all sort of claims. Some of these claims are too ambitious, even at the moment, after 4 or 5 years. Because you see, there's a hype. Once the hype goes around, then everybody runs after the bandwagon just to jump in. Just like the AI, you have seen everybody is doing AI these days. So we must understand, we must be able to sift the hype from the reality. And that's what we try to do today. So, despite there are challenges, one thing is clear. Everybody is after quantum computing. Every major giant is investing in quantum computing. That means something. It means that they are expecting something. And they are basically, most of them, especially big giants, they are investing in a full stack. By full stack, I mean from application to firmware, from software to firmware to the hardware. The whole stack they are building in-house. That gives you another hint. Especially IBM has lost its vantage in the old classical computing. That's why it's very eager now to recapture back its space. Because you see, the first mainframes were invented and commercialized by the IBM. So you'll see that IBM is more ambitious than anybody else amongst these actors to have the full stack, because whosoever has a full stack and whosoever captures the students and the universities and academia and the researchers with that full stack, he will have the early vendor lock-in. And whosoever has the early vendor lock-in, his commercial products will be sold. So this is the idea behind so huge investment going around. That's why you see that the Qiskit is so good, so open, and so well written, and so well invested. And other people are also trying to catch up. The organizations which are not industry giants, who are new entrants like Zenado. I think Zenado name is there. Zenado is mentioned. Zenado is very good. They have come up with the Pennyland framework. Although their framework is not as good, but it is very good for the quantum machine learning. Maybe better than the Qiskit itself. So everybody is now in the game just to have the vendor login and get its pie and a share. This is the volume of quantum effort that is going on. And this is good. By the way, the map is from 2021. If you can see the source, 2023, sorry. 21 or 23? 21. So just, 23. So it's 3 years down, and you can still find that the craze has not gone down. The pace, the momentum has not gone down. There are shifting targets. You can identify them, but the craze and the interest that has on the investment is coming, and it's still coming in. So this is just the volume of investment going around that was there, or that was mapped in 23 by some financial organization. And couple it with the fact that I explained yesterday also, that this migration is inevitable. If it is not qubit, it has to be some quantum tech related thing. The transistor has to change. For sure, there is no other way around. Transistor as a switch has to change. Whether they change it with the probabilistic bits they are in multiple secret data. You change it with the probabilistic bits. You change it with the Q bits. You change it with some other novel, technology, which will definitely involve the quantum tech, which will involve the quantum effects and the quantum tech. So the thing is going to change. So the migration is definitely inevitable. And why it is inevitable? You saw one fact yesterday. Once I connected it to the AI, you saw that, and even on an exponential scale, the compute power needed by the AI model is exponential. So it's an exponential on an exponential scale. Imagine how fast their compute requirement is growing. It is not possible from the energy perspective, sustainability perspective, and neither from the compute power perspective, to serve these models anymore. you have a large kind of supercomputers and data centers serving these, but there's a limit to it. There's a limit to what we can do on the earth with the available energy resources, because there are other uses of the energy also. We use it for the transportation and everything else, and there's an energy crisis going on right now also, you see, with the wars and everything happening. The other is the physics argument. The physics argument is that the Moore's law, which was basically, here is all, you also see a exponential scale, a logarithmic scale, but you see that here the Moore's law is a straight line. So actually it is an exponential. If you take a linear scale, the Moore's law is basically an exponential of that. Here it is shown as a linear line. But you see that it is initially the Moore's law is continuing, but the compute power is not continuing. The compute power is basically stagnating. What can be the reason for it? Anybody can identify the reason from this graph. The Moore's law is continuing here also. From here to here, Moore's law exponential scale is still continuing, which is shown as a linear line on this log scale. Why there is a plateau which is occurring here? This plateau has something to do with this plateau. This plateau has something to do with this plateau. Can you understand the problem now? This is the problem I mentioned yesterday, the thermodynamic argument. You are generating so much heat in the switches that you cannot take them out. And since you cannot take the heat out at enough speed, the thermal performance is less, and you are cramming more and more transistors. What is happening is you have to run them on a lower and lower frequency. That's why you see, since on the last 10 or 15 years, the clock speed of the processors is stagnating around 2 hertz. The maximum is 3 hertz, 2 to 3 hertz, between 2 to 3 hertz. High performance is around about 3 hertz, and the low performance is around 2 hertz. So between 2 and 3 hertz, you find all gigahertz. You find all kind of processors working. So it has stagnated there because you cannot take the heat out of those chips. So thermodynamic argument right now dominates. But even if we forego the thermodynamic argument, the miniaturization that is happening of the transistors here will lead us to a scale where the quantum effects will come into play. So even if it is not heat extraction, the next problem will be the quantum effects. So we have to incorporate quantum effects. Either it is done to the nanoelectronics. The one approach was nanoelectronics, which is still going on around, and it's not finished. But the parallel approach is to utilize that quantum effect to our advantage in form of few bits. That's what the quantum computing people are doing. By the way, to work around this, first of all, we invented, in this graph you can see, we invented a concept of the logical cores, separate cores. You have multiple cores on the CPUs also now. In GPUs, you have a lot of cores, CUDA cores, but in even CPUs, you have 32, 16 cores at the moment in high-end GPUs. And right now, the concept is coming of the chiplets. You're combining different chips together, and then you're trying to increase the speed through the networking, onboard networking. But still, it has a limit. Every solution to this problem has a limit, physical limit. That is why I'm saying that this transition is inevitable. And at the same moment, while quantum computing, due to some reasons, the challenges we'll see, in the later last part of this lecture, still quantum tech is very much in. Much of these, you see, quantum tech things, you see, are already quite mature on the technology readiness level. Technology readiness level is a kind of a framework defined by NASA for adoption of different technologies. So all these technologies you see, although quantum computing is a bit late, you see, it is probably, somehow struggling. Still, there are many other technologies of the quantum communication and quantum sensing, which are almost nearing the wider adoption at a commercial scale. So even if the quantum computing doesn't work, and you have invested your time in quantum computing and quantum information, you definitely have a future in quantum sensing and quantum communication. Although there are roadblocks to that also. That is a separate thing. Moreover, this field is very, young. The AI it started somewhere in 50s, and now, it is 26. So 70, 75 years, almost 100 years. It took less than 100 years, 80 years. So this field has just started in 80s. So just imagine it's only or less than 50 years old. Basically, the emergence happened with this Feynman idea on the quantum computing proposal after this workshop. of this first conference on the physics and computation. There's a Feynman lecture on the quantum computer proposal, from where it started. But since then, while the quantum computers were still not there, there were early on attempts at the algorithms. We are stuck at the algorithms. We are not stuck at the hardware. Hardware is now, progressing quite fast. Right now, what we are stuck at is how to create the use cases from the already available algorithms, which are very limited, because they just showed the power. Shor's algorithm, global algorithm are kind of extreme cases, I would say. You have to invent, come up with a new algorithm to actually utilize whatever is available today, and these do not work. You will be taught these algorithms because as a Kickstarter, that is how we teach the quantum computing these days. So in this workshop, you will be taught both of these algorithms. But rest assured, to actually launch your career into the quantum computing, you need to go beyond them. There are other algorithms like VQCs and everything. But I would say that the main advantage would come once you will try to we'll try to combine the power of the data to automatically generate the algorithms, just like we do the automatic generation of the model in the AI from the data, because we cannot create our own algorithm, we cannot write our own algorithm which can replicate the AI. So here also, personally, I feel, this was one hinge. It is not, probably it will be correct, but probably if you want to search for more algorithm, one approach is, because AI is so powerful. So we involve a quantum machine learning kind of a thing, and we try to discover the better algorithms and with the current hardware, which works with the current hardware. And almost every major area which utilizes with this quantum tech, every major area which utilizes information in some capacity and is trying to address challenging problem, that will get a boost. That will have a quantum advantage or quantum supremacy. We'll discuss these topics later on. You can see every area is mentioned, which is probably, this is just a broader category that I mentioned. There might be more areas to that. So as far as the quantum computing is concerned, the first major impact or breakthrough or dent will happen in the supercomputers, because because the quantum computers are not rivaling your iPad, your laptop, or your palm held devices. What they are rivaling or competing at is supercomputers. So whatever supercomputing are doing today, if we can somehow replace that kind of a thing, partially or completely, with the quantum computers, then we make the first end. That's what the quantum computing is for. And this is the table that shows the advantage for the quantum supremacy, not for the quantum advantage case. Quantum advantage is different. I'll try to. Quantum supremacy is those algorithms which, at the moment, if you try to scale them up with the problem size, they go exponential, right? And you cannot, like factoring. There is no other way. Classical computers, even if they are supercomputers, they cannot solve it. They take centuries. So at some crossover point of the problem, if you see, at some crossover point of the problem, before this, the classical computer is still able to solve that problem, like traveling salesman problem we discussed, like factoring. And before that, that problem size, that if you try to do it on the quantum computer, it will take more time, in fact. But beyond this crossover point, which is different for different problems, it is different from it varies from hardware to hardware also, and problem to problem also. But there will definitely a crossover point. After that, your classical computer will no longer work, and it will take a lot of time, and quantum computer will take less time. Now the problem is the literature that is being generated, or the papers that are coming right now, research papers. They somehow, I've seen most of them I've seen is basically still working or lurking around this phase. So they are trying to show the quantum approach on a problem, since they are emulating. Most of them are emulating, because the real computers are very noisy, so they're trying to emulate. So since they are emulating, what happens is that quantum approach is even slower than the whatever they meant in the paper. That is even slower than the classical approach. So there is no sense. Although it shows that the quantum thing works, or it gives the result, but it doesn't show that it is advantageous. So that is the right at the moment. The research problem is, the research dilemma is this. When I say that the quantum computers will take on the first dent on the supercomputers, this is what I mean. These are the applications where quantum computers is actually today making progress and making a dent. The very first is the chemistry, drug chemistry or quantum chemistry. Quantum computers are making a dent right at the moment, right today, and at these problems. I'm not talking of tomorrow. I'm not talking that there will be a QKD one day. I'm not talking that there will be a quantum computer one day that will solve the cryptanalysis problem. I'm talking what is happening today. So this is where the quantum computers are working, very much working. This is where we are trying. They are not yet working, but exactly this area we are trying to work, because I introduced you to CFD expert or CFD expert in the quantum computing lab yesterday, Dr. Imran. So this is the area that we are trying. Although we are trying this area also, but we have lesser students in the science interested in this area. This area we have expert also, and we have students, so we are trying to this for this area, and we have funding for this. And this is the area, the material discovery and the future, which probably will be immediately following this CFD application. If you can do the CFD, then probably this will be the next jump. So this is for real. This slide is what is real, and this is apart from the myth. Quantum communication, quantum networks, quantum key distribution. At the moment, they are quite methodological, because I mean, if you even implement a quantum key distribution, you have seen the paper, the quantum key distribution is implemented at 1200 kilometers, 1500 kilometers, but the data rate is so slow that they serve no purpose. They are just technology demonstrated at the moment. Whatever China did is a technology demonstration, and Europe has done it much earlier, although not at that scale. Europe and USA has done that thing quite earlier in the metropolitan area networks, not at that scale through satellites, but they've done. But the data rate in both cases are so slow. In European case, it's a bit higher, but in Chinese case, it's so slow that it serves no effective purpose at the moment. There are challenges in that. In quantum communication also, in quantum sensing also, in quantum computing also. You saw that quantum computing is the last amongst the to take the in the lead. But here the quantum computing is working. That's why I showed you this slide. So summarizing this, what I foresee is that the quantum computer will replace us, not exactly replace the supercomputers in data centers, but there will be a hybrid approach. The classical and quantum will go hand in hand, and first of all make dents in the areas which are compute intensive, like large AI models, foundation models, probably those areas, because they work on the probabilities. We saw that they work on the probabilities. You yesterday saw by a clear example, hands-on example, that work on the probabilities. And then the scientific computing, like I talked about the CFD, biochemistry and everything, drug discovery. And then there will be broader applications of the quantum technologies that, like, I mean, they will follow quantum communication, cybersecurity, cryptanalysis, and the quantum sensors, maybe at a later stage, once we'll have mature quantum computers and quantum technology. So even right now, the barrier to entry is high also and low also. How it is low, I've provided how early access is possible to these things. IBM, Amazon, D-Wave, they have offered. In fact, D-Wave offers cloud access to many of the other hardware vendors. So they have one platform, Amazon Brocat, which finally handles everything. In which, I mean, they offer multiple, like Rigetti and other computers, right? In fact, the IBM computers also, increase also. But that is a paid access. Apart from that, there is academic access offered by the IBM. D-Wave is currently not offering access to the region, including Pakistan and China. So unfortunately, in Germany it was available, and it was the earliest one. In fact, quantum annealing computers was the earliest one. And they are still very good for the optimization purpose. Probably the D-Wave is the best. If you ask me for the quantum machine learning, the Synado will be best, but they are only good for the purpose for which they are designed. So they are not general purpose. Both Synado computers and photonic computers, which work on the Gaussian bosonic framework, and as well as this quantum annealing, they are not general purpose. They, I mean, can replicate the quantum universal quantum model of the gate model in certain senses, but in not all cases. So they are best. One is best for the optimization, and the other one is best for the quantum machine learning. But IBM is more general purpose. IBM, Google AI computers are, because they are trying to apply the quantum error correction also to make them even better. So right now you have called cloud access. You can have the cloud access to these computers, and you can, as well as you can emulate, which is more important. Emulation is more important, because yesterday I told you that first we emulate and then we go for the cloud access. This is, I mean, a universal thing. we cannot go for the cloud access with a circuit that doesn't work, because we will not see what is happening once we will get the access to the quantum computer. You just give it a circuit, it will implement it, it will give you back the result. Where the things went wrong, the debugging will not be possible. Debugging is only possible once you are trying to test the state through the emulation and checking the state at every point, what is happening with the state. So first, in a prototype, we do the small scale. If it works, we take the prototype to the actual computer and then see, and then we can scale up on the actual quantum computer to cloud access, and then can see. That is how the approach in quantum computing. And US and EU are, I mean, without any doubt, without any second, I mean, comment, they are the leaders. Even I would say US is the leader, EU is only following up for quantum computing. This remark is reserved for quantum computing. As far as the India, China, and Australia are concerned, what they are trying at the moment is to make their workforce quantum ready, and that is the best they can do, especially India. And this is what the way forward probably for Pakistan also is. I mean, that is the best thing we can do. Produce as many quantum programmers for the use cases. For the use cases, not, I mean, the hypothetical that I've run the show algorithm, I've done this thing. For actual use cases, try to produce the programmers that can run for the actual use cases. Some specific domain like cybersecurity, like I talked about the drug discovery, like I talked about the CFD, some actual application. So, having summarized once again the advantage or the quantum computing benefits, I'll come back to the requirements for the quantum hardware now. Although generally there are 7 requirements, 5 main requirements for the quantum computing and 2 generalized requirements which are further added for the quantum communication part or distributed quantum computing, and they are called the De Vincenzo criteria. But I have tried to summarize those 7 in these 3, and in fact added the middle one. The middle one is not mentioned by the De Vincenzo. It is implicitly implied in the De Vincenzo, but there he is not mentioned the middle one. So the left and right ones are basically summarizing the 7 criteria. So what we saw yesterday, we need to have a quantum register first of all, add qubits to that register, build a more powerful representation of state. Only then the quantum computer works, right? And the scalability is the challenge at the moment. And how to arrange those qubits, we'll shortly see. The scalability as well as how to arrange those qubits to access them, or how to access them. So that is the main challenge at the moment. Then that is why today's quantum computers are called noisy intermediate scale quantum computers. Intermediate scale is this part. This part is intermediate scale, right? The second part is no cloning. Of course, I mean, you have to understand that your register will sit over there on the chip. It is only that register, and all the activity is happening classically from the outside. You can make circuits and put it on the top to do the thing. I mean, you can make a top layer and further layer and further layer, but at the bottom layer, the registers are sitting idle. I mean, there's a one single register that is holding everything, and you are applying step by step on that register, because you cannot clone. If you clone, you have a new register, but the old register is lost. In some cases, we do move the qubits around for say accessing the topology better. In certain cases, we have to copy the qubits, certain qubits, because one qubit is not topologically connected to other qubit, but then that qubit is lost, and that has to be reused. So topologically speaking, the qubits sit over there, and you perform the operations on them step by step. So those circuits, you have separate them in layers, and every layer is performed on those registers that are created. And the last part is most important. You need to have the ability to control as well as measure accurately, precisely control and measure. And it at the same time, once you need the ability to interact with the system, you also want that the system do not interact on its own, which is called decoherence. So you want that the system should be, once you want, you will be able to control or measure the system, but it is not like that once you do not want, the system is still interacting with the things around, which will cause decoherence. So these are 2 competing criteria. So this is what the main challenge is. I mean, the scaling and then this thing are the main challenges in the hardware. So these are the general technologies which are available right now, but I'll only focus on the superconducting because that's what we are working on in NUST, and that is what from a computer science perspective I am interested in, because it's working. It's scaling. Rest everything, if I built an iron trap, I mean, it's such a huge thing to just align the laser itself. It can be, I mean, for cold atoms, for iron trap, it can be physics novelty. Maybe you can publish a paper in physics journal, but for me, for practical purposes, it is of no use. A cold atom quantum computer or iron trap quantum computer, for me, it is of no use. For me, the use is of the superconducting quantum computer, if somebody can come up with or give me the cloud access. Because I'm a computer scientist, I have to use it. And whatever is, I mean, at the moment, making headline, actually, that is superconducting, like IBM, like, I mean, Rigetti, everybody, I mean, even DBA computer is superconducting, using the quantum computer. So the major portion or chunk is dominated by the quantum superconducting. So we'll talk on that technology. Although, I mean, if we can somehow do this part, this last one, the semiconductors and condensed matter quantum computers, other condensed matter quantum computers, especially the last one, NV dynamics, they are still very interesting because they are also scalable. But still, I mean, they are struggling, these are struggling, and these are, at least they are struggling, but still leading. So we will discuss these. This is what the superconducting qubit looks. It is basically based on a Josephson junction, which is basically a nonlinear inductor, which acts as a nonlinear inductor. Why we, I mean, create it and use it as a nonlinear inductor? We can create, first of all, we can create a very small inductor. We can have small stray capacitance, which is there already somewhere, I mean, in the cables, in the setup itself. And then we need inductance that we have to create. So we can create small quantized inductance to it through Josephson junction. That is the main advantage. Is that it allows us to engineer the quantum well. You see, here is the quantum well. If we want, there is a theoretical quantum well, which is this, which is basically, if somebody can recognize this quantum well, because most of the people are from the physics background. What is this quantum well, which I am highlighting? This is harmonic oscillator. Good. So what is the problem with harmonic oscillator? If you can identify, if I want to use this harmonic oscillator as a qubit, will there be any disadvantage or a limitation? Anybody can identify? So we can use this ground state and first state. What is the limitation in using it? Explain. Good. Good answer. Accurate answer. Precise answer. In harmonic oscillator, all gaps are constant. Same gap, band gap. So you are not sure once you apply the pulse whether the things will jump from here to here or here to here or here to here or here to here. You need to engineer this gap, right? And this is what is done by the, if you use a normal inductor, this will be a harmonic oscillator. But if you introduce a non-linear oscillator, basically, which shapes this energy well, it doesn't keep it like, I mean, the harmonic well, but it shapes this, I mean, this harmonic well non-linearly like this. Then the first two energy gap, every two energy gaps will have a different spacing. And we'll try to design this lowest energy gap according to our requirement. This is our 0-1 case. And we try to design it according to our requirement. And in fact, we design it separately for every qubit. This is interesting. Probably, I mean, I don't know whether you know or not. Every qubit is addressed through a separate pulse, which is tuned to its energy gap. So there is a slight difference for every qubit. We craft or engineer this band gap separately for every qubit. And that is one problem with the scaling. I mean, they are so close once you craft them. And generally, this energy gap is of the order of 5 or 6 gigahertz in a microwave range, which we create. This is an artificial atom. We are creating a kind of artificial atom or artificial quantum state, which is called a macroscopic quantum state. That's why, I mean, the people got the Nobel Prize last year, right? They don't mention they have done something for the quantum computing or the qubits. They mentioned that they have created something at the macroscopic level. They have displayed the quantum effect, something like this. The statement says this, the Nobel Prize last year, physics state Nobel Prize. So this is that macroscopic quantum well that they have created using Josephson junction. And by the way, the team is still employed in Google AI and IBM. Those same people are working with the Google AI. So 5 or 6 gigahertz, and this 5 or 6 gigahertz puts a limit on how we have to operate it thermodynamically. And can anybody identify this limit? This limit, that it should be around the operation of this device or junction should be around 250 millikelvin. In fact, lower than that, but around 250 millikelvin. Why? And how I have come up with this number? Anybody who can describe how this number has arrived? I mentioned something yesterday. Dr. DT also mentioned something yesterday. For the bath degrees of freedom, and correspondingly it's an entropy. Anybody remembers? Energy partitioning. Yes. So can you derive this thing now from the KBT factor? The noise floor is KBT, let me tell you, of the environment. It's very easy, it's simple. I mean, all of you are physics students. You can open the laptop, or I mean, it's open. I mean, it's an open books test. You can use your mobile, laptop, whatever you want to use. Arun, you should know because you are working on the hardware, and you have answered it last time also. And now you don't remember, I think. What was your answer? Anybody? Okay, I mean, let's not waste time then. It's simply that noise floor cavity, right? That energy partitioning which is there in the bath. Equalize it with the HF, and then try to derive T from those. Fix the F. H is known. H is a constant. Kb is a constant. Boltzmann constant is a constant. Drive the corresponding temperature, and that temperature comes out to be this. In fact, for all the microwave devices, even if they are not quantum, even if they are classical, we need to define their performance with respect to the noise floor with the same formula, KBT. Even for the low noise amplifiers that we use for the dish antennas, for amplification of the satellite signal, we use the low noise amplifiers. They have to be operated at certain temperature just because of this reason, non-noise floor. And we use the same formulas, the quantum formulas in there also, in the classical domain. So here you can see that they are relevant in the quantum domain. In the quantum domain, they are very much relevant there. So we have to run this thing so that, I mean, at this temperature, there will be a lot of jumps, unwanted jumps. So this thing will be switching. That's what the Dr. DT yesterday told, day before yesterday told you, that as we approach this limit, there will be more jumping. It will be unstable state. So we have to work much below this temperature. So normally the temperature we choose is 4 millikelvin, around about 4 millikelvin, 4 to 6 millikelvin, which is much lower, almost 2 orders of magnitude lower than this. So the first limitation that comes from this is that we need a cooler to reach that temperature, and this is that cooler. What you see in the pictures is not quantum chip. What you see, I mean, glittering thing you see in the picture is basically either the lines, microwave lines, which are interfacing, or this cooler. This is a stage cooler. It cools in stages. First stage, second stage, third stage, and finally it reaches at the bottom line, which is somewhere at the 4 millikelvin. It cools down in stages. And this is the most costly component in the entire quantum computer. Rest probably we can do in Pakistan. It's not that costly. That needs mind and expertise and technology. Rest probably is possible because even 5 gigahertz, 6 gigahertz, even the equipment is not banned. It is, I mean, satellite grade equipment that we can have, the characterization equipment we can have. We just need expertise for that. But this part is costly because we have to import it to bring something to 4 millikelvins. That's why we are not working. If somebody asks me a question, instead you ask it at the end, I've answered before. This is the costly part. Get us this costly part, and I mean, we can do something. And apart from that, there are other requirements also. This is just temperature requirement. The other, apart from this cooling requirement, there is EM shielding. We'll, I mean, see the EM shielding in next picture, in next few pictures. Vibration shielding. That's why it is suspended from the wall, not, I mean, placed on the ground for vibration shielding. There are quantum amplifiers which you can see over here, which basically amplify the signal. These are the quantum amplifiers. So they amplify the signal to an extent that you can actually read them. Normally they're used for the reading, and then there is the classical control of the quantum or qubit, which are these lines which go and control the code. So once this qubit is created, we need to create a superposition, right? Otherwise, without that superposition, there is no use. First there will be superposition, then there will be entanglement. For superposition, we'll also need the gates, and for entanglement, we'll also need. For entanglement, is also a kind of a controlled superposition. You see, you are controlling XOR gate. So you are basically controlling a NOT operation there, a phase reversal there. So there also you are basically controlling the rotation, but there it is a controlled rotation. You are controlling this rotation on this qubit with respect to some other qubit. So in general, we can perform all kind of rotations on this qubit, on this sphere that we discussed yesterday. This is just one standard rotation, but if you see here, a random rotation can be decomposed into 3 parts and can be performed one by one, like you see here. So this is just a rotation that is happening on the block sphere, but it is not that simple. In fact, first of all, you have to generate a pulse which is in Rabi oscillation with this qubit, so that it tunes in, and then you adjust the amplitude and the duration and the phase of that pulse so that it performs the particular rotation. That is how this rotation or gate is implemented. There are pulses, quantum the regular microwave pulses that are going down at the frequency, at the resonant frequency that I created by engineering the band gap at the Rabi oscillation. And then once those micro pulses come, they basically generate either the superposition or the controlled superposition. If they are dependent on some other reading of some other qubit, coupling of some other qubit, then that is a controlled rotation. Okay? We'll just shortly see how that coupling is created. So this is the layout, how the quantum chip looks like, superconducting quantum chips look like, right? So you can see these are the Josephson junctions. This is a 4 qubit case. These are the Josephson junctions here, and then there you will see a lot of resonators, microwave resonators or couplers. So the couplers are the ones you apply the pulse through these outside contacts. You apply all kind of pulses through these contacts. They go through the micro resonators. Those pulses, either these micro resonators are tuned to let go only those pulses which are of the Rabi oscillation of this qubit, so that nothing else gets connected or coupled. That is for this purpose. And through the same, if you design the pulse in a particular way, either it reads, or through this coupler, say this coupler, depending on the pulse, because if you have created a pulse on that works on the difference of the resonance of this and this, then the pulse comes from here, and actually through this coupler, its cells are weak probably. I can have another pointer. Excuse me. Can I have another pointer? I think the cells are weak. It is stopping after something. Okay. Anyway, through this coupler, then the C0 operation or other entanglement operation happens. But actually, everything is not on this hardware also. As there is a software part also. That pulse, how it is designed. Together, they determine what operation is performed. So exactly at the physical level, you are actually using the software also, not only hardware, which is there. Software is also very much important. That's exactly create your replicate your hardware or the quantum gate. By the way, if you are reading it through a pulse, then whatever you read, you have to first simplify it. That's why you use these quantum amplifiers. So right now the scaling challenge is, there is definitely a scaling challenge. First of all, the scaling challenge is the reason how many qubits you can place, and then how many qubits of them actually connect with each other. Not every qubit connects with every other qubit. In your circuit, once you design your circuit, you do not care whether some qubit is connected to some other qubit or not. You just let it go. You say that connect this qubit to this qubit, control this qubit from this qubit. But it is not that easy for the processor. For processor, it follows certain topology. Sometimes, but the qubits you entangling, processor is unable to connect those qubits. So what it does is it keeps some extra qubits, always extra qubits, and once it transpiles, it shifts the qubits around, so that whatever operation you are asking for from it, it is actually performed. And since the hardware and transpiler are not that precise and good at the moment, sometimes it happens you write a circuit and it not actually implemented as such. something else is implemented. And so that's why many people today claim that they are not getting the results, because they do not counter check after transpilation, but they are actually transporting to the circuit. Always transpile for the hardware, respective hardware, and then cross check what that transpiled circuit is. And then you will probably be able to show that it actually works. Okay, this is the reason. And the second thing is, if you see these many lines that Dr. Didier talked of yesterday, with so many lines going in and patches and everything around, and so many interfaces, how many qubits can you put? There is a limit to that, physical accessibility limit. So if you reduce the, say, the lines, number of lines and everything, maybe you are better off. Probably the scalability will improve, not by orders of magnitude, but at least a single order of magnitude is definitely possible. So this is the main limitation at the moment for the hardware scalability. That is why we are stuck. That is why we are stuck at the moment with this 1121. Actually, these 1121 qubits are actually 1024. Keeping the extra qubits around that I said. Actually, what you can use is on this processor is 1024. They have, kept some extra qubits, because you see the qubits should be power of 2, right? Why they made a GPU with 1121? Just for the reason because 1024 will be used, rest is extra qubits, and then they are used for the to cater for the no cloning and shifting the qubits around, right? And then connecting them according to the topology. But after reaching this limit, people have stopped working on the scalability problem at the moment, because what they realized yet, even this with this scalability, which is quite enough at the moment, the physical qubits are too noisy. So the whole focus now, at the moment, the shift has shifted in recent years. After this last, it is probably, in 23 that happened. This highest scalability that they achieved. After that, the whole focus is towards actually the error correction. Somehow, last year or this year papers are on error correction. Error mitigation and error correction, that is now the current area at the moment. Because once that is done, then probably then again shift the focus towards the scalability and try to improve the scalability part. And the other thing is that people are not now these days are not focusing on the quantum qubits count, but actually they are now claiming for the quantum volume. How many qubits and how how much depth you can use those qubits without decoherence and getting enough results. Okay, how much is the depth of the circuit multiplied by the bits or the number of qubits is called quantum volume. So this is what is going around. In the firmware and this is a complete stack of the computer that I've shown. And Dr. Detail was telling about this thing to reduce the number of lines. What they're trying to do is right now they generate the pulses on externally. They generate the pulses, and then through lines, through cryogenic input-output chain lines, they basically affect the quantum processor. What they're trying to do right now is to have this control electronics, embed directly onto the chip. But for that purpose, this control electronics have to work at the 4 millikelvin range. So that's why he was talking of the cryostatic or cryogenic CMOS device. So cryogenic CMOS technology will probably allow this electronics to be shifted directly on the top without those lines. And once you reduce those lines, you improve the scalability, because too much lines always create a problem. Interference also, crosstalk and everything. So what we are doing at the moment, in just for your interest, what we are doing at the QCell at the moment is this part. This part and this pulse part. We are trying to work this out. Definitely, we do not have the rest of the. We will try to integrate it at a later part with the National Chip Design Center, which is there in the NUST, which will go for the chip design. But first of all, we're trying to build something using this pulse design, as well as the electronic simulation, the electrostatic simulation of the qubits, and then its simultaneous generation. And applying this simultaneous generation is important to be controlled by these pulses then. So this is the area that we are actively working on. And this is what the actual quantum computer looks like, superconducting quantum computer. Actually, if you have say ion trap on some of the computers, the size is almost same, and limitations are more because they use very aligned lasers. But in this case, those alignment of laser and everything is not that important. But the scale or the area occupied is almost same. In fact, less. I would say less. So this is the chip. Chip is somewhere at the bottom here. Here, sorry. This place. on which the qubits are there and the resonator and everything. Rest are the lines for the measurement and control pulses. This is the measurement line through the quantum amplifiers. And then this is the microwave stack, which implements everything, complete microwave stack. And it is controlled through classical computers. All the pulses and everything is controlled through classical computer. And once you do the cloud access, you are actually accessing this part. You are giving the program to this part, which has to implement this through these microwave rack. Implement the program on the chip somewhere over here. And rest, this hanging part is for the vibration control. Then there is a shielding also outside that I'll shortly show. So this is the shielding. This is the shielding part for the EM, right? So this is the vibration hanging part is for the vibration. This is the EM shielding. Temperature is being controlled by those multi-stage dilution coolers, and that's how the chip is working. And what I didn't show over there is this cooling arrangement. Here it is shown. This is that cooling arrangement. This rack was not shown in the previous picture. This is the cooling arrangement. So, why to have such a huge computer? Question is obvious. If I can have a laptop, a desktop, why to go for such a huge thing somewhere and which has to be cooled also? So much factors and limitations to be taken into account. Infrastructure to be built. What is the use? Compare with these two. The mainframes in their early stage were almost as big. In fact, bigger. If you have seen the NEX picture yesterday, it was even bigger than what I showed you as a quantum computer today. And even today, the computers we are trying to replace are even much more bigger. This is a frontier supercomputer. You see the racks, and this frontier supercomputer cannot implement more than 50 qubits. So if we can logically create, say, 51 or 52 or 60 qubits, we are already beating this giant on certain problem. So the thing will be utilized through cloud access, and the infrastructure it will replace is this one, the current one. So there is no surprise in it. And maybe, I'm sure with the passage of time, it will be miniaturized also further. Whatever you are seeing in the picture, it is now at this stage. And once the regular computer has been miniaturized from this to the laptop, and it's even better, probably one day you will see the quantum computers also miniaturized at scale. Maybe reaching this scale or even further. So I already talked about the quantum, this transpilation part. Just to make to emphasize this, whatever circuit you make, there is a language which is called quantum assembly language. It is universal. It is agreed upon by many of the computers. So whatever you want, first of all, whatever circuit you make, change it to the quantum assembly language for the particular hardware, and then cross-check whatever you have got whether it works or not. That is an important step in my opinion, in humble opinion. Because what people normally do is like they say write program in Qiskit and then just throw it on the Qiskit QPU and it doesn't work, right? So because there are many constraints, right? Like I told you, constraints on qubit connectivity, and then every gate what you have created in your perception, you have created a CNOT gate. It is not implemented like that on the quantum computer, superconducting quantum. Every quantum computing technology, whether it is ion trap, superconducting quantum computer, photonic quantum computer, annealing quantum computer, it changes whatever you have done into its native quantum operations. So those native quantum operations are important, but they're used. By the way, this QSM will not show you the native quantum number. This is only first part. This is only the compilation part. The translation part happens after this, which actually change to the native gate set. You do not see the native gate set, but still, a part of the problem can be seen if it is there. The QSM hints upon at least a part of the problem if there's some problem with your compilation part. So, just trying to finish my lectures. These are the last two slides. I hope I have time left, sir. Close. So let's just, I'll just quickly go over them. Decoherence is the thing. There are two kinds of decoherences that occur. You can see those decoherences on the block sphere itself. If you have some, coupling or noise over here on the x-axis, then a longitudinal decoupling or T1 decoupling happens, in which the phase flip happens. For example, if you are having one, it will be flipped to the 0, or 0, it will be flipped to 1. Normally, the 1 to 0 flip is more important. 0 to 0 to 1 flip normally doesn't happen because we have already constrained the energy, external energy. We are not taking the external energy, so it is one way normally. But this is what the longitudinal flip or the phase flip error is. The other thing is, if we have a coupling on the z-axis, that coil basically tries to shift whatever state you have along this axis. This is called dephasing. So normally this dephasing, which is a T2 error, and the first error I mentioned, the longitudinal relaxation error, energy relaxation error, longitudinal energy, these are mixed, and it is called a transverse error or transverse relaxation combined, dephasing plus longitudinal relaxation. So these two errors are normally combined, but they are reported separately. T1 and T2 are normally reported for the computer separately. And what we are trying to do at the moment is, in our lab also, is trying to create the error correction codes in which we use the multiple qubits and then try to nominate certain qubits as inspectors to judge the neighboring qubits. And if the neighboring qubits are getting some errors, so then we apply the pulses, control pulses accordingly to reverse that error. So this is what the entire concept of the quantum error correction is. We have an overhead of the qubits, but those overhead of the qubits is basically used to correct the errors by observing. First of all, they are entangled, and then by observing certain neighboring qubits, we try to address the error through external control pulses. This is what the entire idea of the surface quantum code is. There are other approaches like quantum low density parity checks, which use less overheads in the number of the qubits. And there are error mitigation techniques also, which are separate from these. Like I think one was mentioned yesterday, the dynamic decoupling. So these all are there, but we're trying to apply these in our lab also. And this brings us to my end of my lecture. My story is starts and end on these lines. I hope and it helps you judge your own path in the quantum as well. By the way, this is a picture I took in Kaiserslautern, and these two paths and the Rhineland Pfalz forest, which extends from Germany to France, it's quite wide forest. So once I stood over there, I took this picture just with these lines in my mind. So taking the unused path or less used path has made all the difference for me, at least. And a final word, that the quantum computers are coming, and no army of the world can beat the technology that is coming. And I really mean these words, because I mean it is since the era is of information warfare and everything, nuclear war is now over, or maybe will not be resorted to. This technology has a potential, because you see it has also an exponential potential, just like the exponential potential of the chain reaction. So if we timely invest in this technology, we are actually catching up, and no other army which is lacking this technology will be able to meet the challenge. Thank you very much.
Well, our next speaker is Dr. Madhya Khalid, and she is an assistant professor at NUST, School of Electrical Engineering and Computer Science. And she did her PhD on the topic lightweight cryptographic protocols for securing IoT and edge devices. She is very much working in applied cryptography, hardware security, and quantum cryptanalysis. So here I invite Dr. Madhya Khalid.
Assalamu alaikum, everyone. Before everything is set up, thank you so much, Dr. Hamad, for the very great presentation. I would really like to build on Dr. Hamad's presentation. I reckon most of the students are from physics. How many students are from physics, if you can raise your hands? Okay, so we'll have to reevaluate what we're going to do. आगे और पीछे होगा ठीक हो गया और पेन का भी पता पूछना
हाँ वो they're saying Zoom link से access
पेन कैसे यूज होगा स्क्रीन के ऊपर हाँ
जी लिखने के लिए
दिखने के लिए ये तो ये हो गया
पेन तो है
स्क्रीन पे साथ है तो मैं
इसको
अगर मैं
ये उस पेपर क्योंकि ये एज अ इधर सेटिंग हो रहा है ना सेटिंग करनी पड़ेगी
हाँ अगर हो सकता है सेटिंग इसकी अगर सेटअप कर सकते हैं सो बिफोर वी स्टार्ट अगर आप स्लाइड 2 साथ करते हैं तो तब तक मैं उनसे बात भी कर लूँ सो the flow of my presentation would be slightly different. Dr. Hamad very well talked about how quantum computers work, what is the hardware, what are the limitations. Me as a computer scientist, I'll present you a different perspective. Now, assuming that you have a good working quantum computer and you have a front end and you have a UI and you need to code this and you need to get something sufficient or something good out of it, irrespective of what's happening in the background, I'll tell you that, right? Sir Hamad very well said that superconducting computers are being used. So I'll be using IBM setup so that you can actually simulate them. But before simulating them, my core purpose would be that you have a paper and a pen, you have a circuit, so you should be able to solve it on the paper. So this is the key takeaway of my lecture. So there are 2-3 things that I need you to do. Number one, you should have your paper pens ready. Number two, if you have a computer, please get the computer. And number three, if you can come up with the slides. Number three, I'm a little bit pro interactive session. So Varda here is my RA, and we have certain quizzes at different slides. So you'll have a QR code scanned here, and it's a timer kind of a thing. So you'll have 1 minute, and then you'll respond to that quiz, and then we'll move forward. So take a minute, have something with you. I just need your basic mathematics skills, which I'll refresh, and then we'll work on it, okay? And if someone thinks that the pace is too fast, do let me know. Me and Varda are here to help you. The next slide करते हैं वो एक मिनट लो अच्छा next slide अगर करते हैं तो वैसा कुछ okay जी so there are two QR codes here मैं online भी audible हूँ ना okay so there are two QR codes available. Those who are online available with me are requested to please scan only QR code 1, and those who are on site with me are requested to scan both the QR codes. Now, the first QR code is basically IBM Code Composer that gives you a drag and drop option to solve the circuits. So it will give you on-spot testing of what you have done. And the second QR code is basically a platform for the online quizzing. So you all have to log on to that, and whenever you see a minion in my slide, you have to act on a quiz. So minion means that you need to give a quiz. So let me know whenever you're ready. So QR code 1 is for IBM Composer, and QR code is for the quizzes. All the online users are requested not to scan QR code 2 link. The reason is that we have limited number of users we have. For the online class, I'll give you the quiz at the end of the lecture. So all set? Everyone set? Shall we start? No?
only 6 people joined.
Okay, sorry. But there is one, so only 6 people have joined QR code 2. So you're requested to please scan QR code 2 so that I can see that at least the participants in my class have that code. My apologies, this lecture is going to be very interactive. How many?
10.
10. So I'll give another 30 seconds because that will be eating up my time. 12? What happened? Don't want to study? Don't want to give a quiz?
Easy question is the मुश्किल
हाँ,
नहीं quiz
I promise Varda has made easy questions. Okay, ji. Maybe you have an online link available on the slides as well. So you can get a link from there as well. Or Varda can help you, so you can come up to Varda and scan. So I would like to now start the lecture. Okay, ji. Starting with okay, cells for a वहाँ connected है ठीक हो गया okay जी so for the next 2 days I'll be delivering different parts of lectures and for those lectures there'll be 4 different things that I'll be discussing. One is quantum circuit, then the 2 specialized circuits, superdense coding and teleportation, and finally the phase oracle design. So the aim of today's class mainly is to understand how circuits work, and once you understand how circuits work, you'll be solving superdense coding and teleportation circuits for me. So, so the first part that we're going to study, this part, quantum circuits, this is very important and this is very mathematical. So starting with today's lecture, so this is the agenda. You have been studying about superposition entanglement from the experts, national and international experts for last 2 days. So I'll be very quick in discussing the quantum gates and superposition, and after that we'll be discussing different solutions to that. So first of all, superposition, as you all know, the small simplest analogy is a coin. Coin in the air is in superposition, and coin when in the hand gives you the deterministic output. So this is the visual representation of the classical bit and a quantum bit. So classical bit deterministically represents 0 or 1, whereas a quantum bit represents 0 and 1 simultaneously. And the mathematical expression for that is a 2 cross 1 matrix. So I'll be talking a lot about matrices. So this is a 2 cross 1 matrix that defines a single qubit. In these qubits, alpha and beta are complex numbers, and alpha mod squared represents the probability of qubit to land as a 0 when measured, and beta magnitude squared represents the probability of a qubit to land as a 1 when measured. So everyone knows that. So you see a minion. That means a quiz is live. Although you see a timer of 2 minutes, but I'll stop that timer in 1 minute. Okay? So you have 3 quizzes just to check your superposition skills. Varda, is the quiz online?
Yes.
Okay. So you can stop the quiz after 1 minute. So on the screens of the quizzes that you have got, there are different questions and you have to answer that is it superposed or not, or what is the probability to land as a 0 and what is the probability to land as a 1. Yes? You can come up to Varda and get it scanned. Varda, my RA is here, so you can come up to Varda and get it scanned. Okay. So 1 minute done. Next question is coming up.
Yes.
So the next question is coming up. So total 3 questions. The second question is coming up. You have the access? You don't want the access? Second question up?
Yes, second question now.
No. Has the time finished? Okay. The third question is on now. And I'll share the results at the end as well. Done, Varda?
No.
Finish the third question so that I can move forward.
It's okay. The questions will be उनके solutions slides के end में आप लोग परेशान
हाँ, ठीक है. So moving towards superposition and in a two qubit system. So we have two qubits.
I think this slide's game with you. Finish 3 questions so that I can.
So all the 3 questions are up. Now I need your attention. So for a two qubit system, so those who have solved all the 3 questions, please raise your hands. Only one. What happened with the rest of them? Two. What happened with the rest of them? Why are everyone so?
Some of them stand the wrong QR pehla wala,
Okay.
and some of them stand.
So I'm so sorry if I just have to move around and if so the third quiz is there. So if you're interested and you have solved the third quiz, so it's done. Now I need your attention for the next quiz. So for a two qubit system, there are total 4 possibilities. What are the 4 possibilities? 0, 0, 0, 1, 1, 0, and 1, 1, right? And as you can see that we have 4 possibilities. So we have 4 probabilities, 4 magnitudes. Each magnitude square represents the probability to land at a certain position. Yes? So we can scale it up exponentially. But again, just to check, there's another question coming up that is regarding the two qubit superposition. Verda,
Yes.
it's on? Okay, so you have next question that is regarding two qubit superposition. So you have a qubit given and you have to solve it. I hope everyone in the class now have access to this. Yes?
अब देखो क्वेश्चन आएगा आपके पास आएगा टाइम नहीं अब क्योंकि मैंने क्वेश्चन कर लिया है यू आर नॉट तो आपने एक्सेप्ट नहीं किया अब जो भी क्वेश्चन आएगा आपको भी देना
So this is a time based thing. So in the given time अगर आप वो नहीं करेंगे तो नहीं होगा और वो गुजर जाएगा. बेटा सेकंड हो गए कंप्लीट? बिस्मिल्लाह. ध्यान से. All the questions done for second slide? Okay, Ji. So I need your attention. So I hope I'll share the results at the end. So now you know superposition, you know two qubit superposition, and you know that the magnitude squared. The important thing to note here is that the magnitudes are complex in number, and the magnitude squares gives you the probability to land at a specific possibility. So this is important, right? So the quantum gates are here. Dr. Hamad and all the other people, Dr. Hamad covers the gates very well. So these are basically qubit transitions. I'm going to give the detail of the basic or the native gates. Starting from single qubit gates, we have poly-X gate. Everyone familiar with that? What happens in poly-X gate? Can anyone tell me what the transition happens on the Bloch sphere? So yes, any other which gives, can you give me the description with respect to the axis on the Bloch sphere? Okay, okay, fine. So if I say that on the Bloch sphere, if I rotate the x-axis, if I rotate the x-axis 180 degree, that is what happens with the next gate. So if I rotate the whole Bloch sphere on the x-axis, anything on the Bloch sphere actually moves. Yes? So we have poly Y gate, poly Z gate, Hadamard, phase gates, control gate. इनको हम बारी बारी discuss करेंगे, but these are the list of the gates that we'll be discussing today. Moving forward, the important thing is that measurement is an irreversible process. ये सारे reversible processes हैं. So measurement is an irreversible process. When a qubit collapses, it cannot be recreated. Okay. So construction of unitary gates. So now we are discussing everything with respect to circuit solution. So the important thing is, there are two important things in this slide. For example, if I discuss poly X gate, there are three important things for you to note down and for you to memorize, right? Now one, if I have a Bloch affair and I'm applying a poly X gate, so what happens is that on a Bloch affair, we have X axis, we have Y axis, and we have Z axis, right? So poly X means that you grab the Bloch affair from the X axis, you grab the Bloch affair from the X axis, and you rotate the whole Bloch affair 180 degrees, right? I hope you can imagine that. So whatever is on the Bloch affair, it kind of naturally rotates it with it. So when we say that X gate is the inverse gate, what happens is, yeah, we actually flip the world upside down, right? We flip the globe upside down, and this happens, that's why the output becomes flipped, but actually conceptually, the whole Bloch affair gets rotated 180 degree, and anything on this affair rotates with it. So one important thing that you need to memorize and note. The other important thing that you need to note down, and you'll be using a lot, is that this is the vector. So if you're not going to solve the question intuitively, then you should know that whatever qubit you have here, you're just going to matrix multiply it to get the final answer. Yes? So I want all of you to write this matrix, because we'll be coming back to this matrix again and again. Okay? And the third important thing is, again, this first column gives you the output of the X gate when ket 0 is applied, and this here is the output when ket 1 is applied, right? So I can say that when ket 0 is applied on an X gate, the output is ket 1, because this represents ket 1, right? And I'm sorry for the online users. And when ket 1 is applied, this whole thing, 1, 0 is the output, which is ket 0. Make sense? So you have to write three things on your paper. One, poly X gates give the Bloch affair rotation of 180 degree. Number two, you have to copy this matrix on your papers as it is. And the third thing is, you have to write that if we apply ket 0, the output would be ket 1, because this column gives you the ket 1 expression. Yes? And when you apply ket 1, the output becomes ket 0, because this column expression gives you the value of ket 0. Everyone with me? So now we're going to discuss the gates from these three perspectives. Okay? So am I going too fast, or is that okay? Because I want you to write everything. Okay? So poly Y gate, same story, different axis. What happens is that you grab your Bloch affair from Y axis and you rotate it by 180 degree. So you rotate the world upside down, right? But now there's a phase of 90 degree, because you're rotating it from a different axis. Yes? Number one important thing. Number two important thing, this is the matrix that you need to note down for the Y gate. If you know it already, it's good, but it's better to write it down. And the third important thing is that if I apply ket 0, I get iota ket 1. If I apply ket 0, I get iota ket 1. Everyone agrees with me or not? Yes? And if I apply ket 1, what do I get? If I apply ket 1, what do I get? Minus iota ket 0, right? So write it down. We're going to need it. Everyone with me? Shall I move to the next slide? Okay. Poly Z gate. Again, move the Bloch affair 180 degree along Z axis. This is the matrix that we're going to use. When we apply ket 0, the output is ket 0. When we apply ket 1, the output is minus ket 1. Minus ket 1. Yes? Yes? Okay, good. So, everyone with me? Written? Okay. Next is Hadamard gate. Again, Hadamard gate actually rotates the Bloch affair, but it rotates the Bloch affair on the axis that is on the xz plane. So what happens is that instead of instead of x-axis and instead of z-axis, we have this kind of an axis, or something here is rotated to this when we rotate it on the xz plane, right? So in one liner, the Hadamard gate rotates the Bloch affair 180 degree on the xz plane. So there's no z, there's no x, so there's an xz plane, and when we rotate it on the xz plane, as you can see in the slides, so this gives you the whole expression and the trajectory of a qubit, right? Okay. The important part here is again the matrix, and we can see that whenever ket 0 is applied, the output is 1 over under root 2 ket 0 plus ket 1. And when ket 1 is applied, the output is what? 1 over under root 2 ket 0 minus ket 1, right? So you have to write it down. Everyone with me? Okay, Ji. Next. Next are the phase gates. So I'm not going to explore the phase gates again and again, because phase gate gives you the opportunity to rotate the Bloch affair along z-axis at a given angle. So instead of 180 degree, I can choose the angle of my choice. So phase gate is the rotation along along z-axis. But that is not the case with what we are looking for. One thing that is important, you should know the matrix. The other thing important that you should know that what happens when ket 0 is applied and what happens when ket 1 is applied. So I would like to request you to take picture or note the matrices so that we can move forward. Because this is something that you've already covered. Yes? Yes? I like a lively class, by the way. Okay, Ji. Measurement, you all know. So we have probabilities if it is defined by C0 and C1. So C0 mod squared gives you the probability to land as a 0, and C1 mod squared gives you the probability to land as a 1. And it is an irreversible process. So once you measure something and you see the deterministic output, you cannot reverse it. So this is the last operation on your quantum circuit. The next gate is controlled NOT gate. Can someone tell me what a controlled NOT gate do? Yes?
Depends on the control gate. If it's the next gate target bit. Sorry, if it's 0, it would want to anything. If it's 1, it would the next.
Yes, perfect. So it's a 2-qubit gate. That means it takes in 2 qubits and it gives 2 qubits as an output. So this is the control qubit and this is the target qubit. So if the control qubit is 0, nothing happens to target qubit. If the control qubit is 0 and the target qubit was 1, the output would remain 0, 1, right? But if the control qubit is 1, the target qubit flips. So if the input is 1, 0, the output would become 1, 1. And if the input is 1, 1, the output would become what? 1, 0, right? The important thing to note here is that this truth table is made from the top to bottom approach. That means that most significant position is given to the top qubit and least significant position is given to a bottom qubit. Now, why this is important? Whenever you're using different simulators, you have to check that how your circuit is being interpreted on a simulator. Is it a top to bottom approach or a bottom to top approach? So this specific circuit with respect to the truth table is a top to bottom approach. That means top is most significant bit and bottom is the least significant bit. Everyone with me? Okay, Ji. I'm intentionally not writing the matrix for this is. So I'll come back to it after a while. Next is Toffoli gate. Toffoli gate, can someone tell me what happens to it? What is it? Yes.
It takes two bits as an input. One the zero then either one is one then
If either one is one, the bit flips.
first two both should be one. Either one is zero then it won't do anything.
Yes. So it is a 3-qubit gate that takes in 3 qubits as an input, 3 qubits as an input, and 3 qubits as an output, right? So these two are the control bits, and this is the target bit. If the value of both the control qubits is 1, then the output would be flipped, otherwise it won't. So in the last 2 rows, you can see that the values of A and B was 1. That's why 110 transformed to 111 and 111 was transformed to 110. And in the rest of the cases, the input and output is same because there's no change in the target bit, right? So again, one thing that I'm skipping intentionally is the matrix for that, right? And you're going to have to write that matrix by yourself at some point of time. Understood? Shall we move forward? Okay, Ji. This is a simple swap gate. Swap gate, Dr. Hamad would definitely say that it's very difficult to do it in hardware because you sort of flip the values of 2 qubits. On a simulator, it's very easy. So you just add a swap gate. It does not have any mathematical action. It just swap the 2 values. Okay. So we'll be using it very less, but again, this is the gate that was given there. So I wanted to discuss it. Now, coming to the circuit. So what do you understand or what comes in your mind when you hear the word circuit? Okay, what generally a circuit is? So it's a pictorial representation of something happening, and it gives you a sequence of something happening. When we talk about an electric circuit, it's generally a closed loop, right? But when we talk about digital circuits, it's basically an acyclic kind of a thing. What does acyclic mean? That it starts from one end and it ends at the other end, right? What you here see is a Boolean function. It's a Boolean circuit which takes 2-bit input, and this input y is then copied into 2 lines. This is a classical circuit, right? So in one line, a NOT gate is applied, and then it reaches to an AND operation, and the other line is inputted directly to an AND operation on the upper end. And here it is another circuit. So this is a simple Boolean circuit that actually performs an addition, right? So you must have seen it somewhere. So you have to solve it logically. So the important key takeaway here is that circuits in computer science are not cyclic, they're acyclic. That means that they start from one end and they get to the other end. So we start from the left here with the inputs and we're getting the output here, right? So this is an important thing. The other kind of circuit is an arithmetic circuit. Again, it's an acyclic circuit. Again, the important thing to note down here is that we start from the left and we end up at the right through performing the operations. Now, why we are studying this? Because this is the sort of quantum circuit that we're going to work with. So given we have a nice working quantum computer, we need to build something on it. So by building on it means that we need to assemble different gates so that certain transformations can happen to our qubits and we get good optimized answers, right? So we have to make circuits for that. So since I'll be using IBM Composer that was given in QR1 link, you can access it through your laptops and through your mobiles as well. Now, the 2 very important things to understand here. Number 1, IBM works in Z basis. What does that mean? IBM by default works in Z basis. What does that mean? Okay. Yes. So whenever we start working with a quantum computer, we need to have an orthogonal basis set. So if we're working with a single qubit system, we need to tell him we're working on a Z basis or an X basis or an Y basis. If Z basis, we're working with the Z basis, that means the north pole is an absolute zero, ket 0, and south pole is a ket 1, absolute 1, and everything in between is a superposition between 0 and 1, right? So one important thing that you have to note down here is that whenever we're working with an IBM system, by default, we're working with Z basis, number 1. Number 2, by default, the initialized values in the IBM system, whether you use the Qiskit one or the composer, by default, the initialized value of every qubit is ket 0. So whenever we initialize a line, we get the initialized value as ket 0. Second thing important, the third important thing is that it follows bottom up approach. This is very, very, very important. Bottom up approach means that, for example, I have 2 qubits, right? In the previous slide, when I was discussing top to bottom approach, I was saying that the top qubit would actually be the most significant bit. Here, it's opposite. Now, as the index says, Q1 is the most significant qubit, and Q0 is the least significant qubit, right? So, why this matters? Because when you're going to read the measurement results, you're going to read the measurement results as if that the most significant value gives you the output of qubit 1, and the least significant gives you the output of qubit 0. So these are the 3 very important things while you start working with the composer you have to know. Because these are the small things, if you skip those, the interpretation completely changes. It works with Z basis, all the qubits are initialized as 0, and we strictly follow bottom-up approach. Okay? Now, I need a volunteer to solve this circuit. Amen? Okay, so we have qubit 0. These are just barriers, okay? So first we're going to solve it intuitively so that you can know that how things happen, okay? So we're discussing qubit 0 only right now, okay? So qubit 0 is initialized to which value? Ket 0, everyone agrees? Okay, now when we pass it through an X gate, ket 0, when passed through an X gate, what happens to it? It becomes ket 1, you have written it on your paper, yes? Now coming towards qubit 1, nothing happens, so we have ket 1 on the top and ket 0 at the bottom. Everyone with me? Now, any other volunteer? Any other volunteer? Okay, amen again. So we have a ket 1 on the top and ket 0 at the bottom, and we apply C0 gate where qubit 0 is the control bit and qubit 1 is the target bit. The value of qubit 1 is ket 0, the value of qubit 0 is ket 1. Now, anyone other than Eamon? What is the definition of C0? Flip your pages. What is the definition of C0? When the control qubit is 1, the target qubit flips, right? So we had ket 0 here, but it was transformed to ket 1 here. That is the control qubit. And we got ket 0 here. Now on the control bit, we have ket 1. And on the target bit, we have ket 0. What happens? It flips. So this remains as it is, ket 1. And we get a ket 1 here, right? And when we measure ket 1 and ket 1 in Z basis, what answer should I get? What answer should I get? 1, 1? Everyone agrees? Everyone agrees? So we have the answer 1, 1 here. Yes? So I need you all to take a minute, take your paper and pen out and solve this, because you're going to solve horribly big questions regarding this. Okay? Take a minute and solve it. I need you to have your key on your with you, the X gate, Y gate, Z gate, the one I dictated you, it should be ready with you. Okay? Solve this, write it. If you have any questions, Varda is there, you can ask her. Or I'm available here as well. So we start from the left, we end at the right. All the qubits are initialized as get 0. We work on Z bases and we study the circuits from bottom to top. So these are the 4 important things. So again, when we start with qubit 0, it is transformed to get 1. Nothing happens here. So now control bit is get 1, the target bit is get 0. Upon the application of C0 gate, we get 1 as it is because nothing is happening here. Control bit never changes, only the target bit changes. So because the control bit was 1, the target bit was converted into 1 as well. So we have get 1 and get 1 here, and we get the answer of 1, 1. Yes? Okay. Now, anyone who's enthusiastic enough and want to test it, you had QR1 as a composer. Open up your composers. You'll get a layout. You can drag and drop the operators. Unfortunately, I cannot open 2 screens here. That's why I can't show you there. Okay? But at the end of the class, I'll show you there. Okay? Now, okay, I need your full attention for about 15-20 minutes. Paper and pen on. Don't need to work with the composer right now. I need everyone's full attention, please. Okay, now this is a single qubit circuit. We're working with Z domain. The qubit is initialized as get 0. We only have 1 circuit, so there's no point of bottom up or top bottom approach, and we have to work on it. Okay? Now, what would happen? There are 3 ways to solve this. One is the hard way and 2 are the easier ones. Okay? So one is you have get 0. First, you think that what happens to get 0 when Hadamard is applied? It becomes get plus. Yes? And then you think what happens when an S gate is applied? I'm not that fluent, so I'll have to think about it. And then what happens when an H gate is applied? Again, I have to think about it. So it becomes difficult, right? So there should be a proper method to it, right? So one of the easiest method and probably the least used method because it's very elaborate, but the tried and tested method is to make, since all these are 2x2 matrices, right? So first H is applied, right? Then S, then H, and then T. So you multiply all the matrices, make one big matrix, multiply it with get 0, and get the answer. Make sense? Right? But here's a catch. Because in matrix multiplication, it is not what do we say it? It is not commutative, so we have to be very specific about the order, right? So the important thing is that when we write the order, you just have to remember that it's the opposite. So first we apply H gate, then S gate, then H gate, and then T gate, right? So although the circuit is from left to right, but when we have to make a big 2x2 matrix that combines all the unitary operations, you have to go in the reverse order and you have to write all the gates in the reverse order. Take a minute and grasp this. In the circuit, pictorially, we move from left to right. We apply the Hadamard first, then S, then H, and then T. And since matrix multiplication is not commutative, so you have to be very specific about the order, right? So we first apply H, S, H, and T. So pictorially, what happens is that we build the circuit from left to right, but we write the combined matrices in the opposite order. Yes? Okay. So now, the second part, I don't want you to do it by yourself. You can ask ChatGPT to multiply all the 4 matrices and verify the result. But what happens is that you have 3 matrices, which we studied earlier. You multiply them in this order, and then you get the final answer. Yes? Now what should happen? Now what should we do? Now all these things are combined together as a big matrix. Now how do we get the answer? So what we do is that we multiply ket 0 with this grand unitary gate to get the answer? Yes? So solve this and tell me the answer. So this is the most lengthy but unfortunately most reliable method. We won't be doing much of this, but you have to know what happens when we do this. Ask your chat GPT to multiply this 2 cross matrix with ket 0. And it's a very simple matrix. You can do it by yourself. And I'll require an answer before moving forward. Yes?
1 plus one of zero two.
Yes? Okay. Now, following that, can you tell me the probability to land as the answer to land as a 0 or land as a 1? What would you do? So amplitude squared here and amplitude squared here. Yes? So I can see the amplitude here is 50%. So 1 minus 0.5 is again 1. So without, doing much of a work, it's 50-50 probability. Yes? Everyone with me? So I need you to write down a statement that whenever you have a circuit, you have two ways to solve it. One is the mathematical approach through matrix multiplication that you have done right now. It's a lengthy approach. We won't be following that much, but this is one approach, right? So whenever you have circuit, you solve it mathematically using matrix multiplication. Okay? But this might be a lengthy process. So now, if you've written, I need your attention again. Okay, now paper pens with you. And I need your key that you made with me with you ready. Now this is the second method which is mostly used and you have to master that skill. It's very easy, but it's nice to solve. So you have ket 0, right? And you apply the Hadamard gate. What happens is you see the first column of the Hadamard matrix. See your notes. The first column of the Hadamard matrix, right? You wrote that now? You wrote that on your papers? So ket 0 became 1 over under root 2 ket 0 plus ket 1. And this was actually the first column of Hadamard gate. I can show you. So this was the first matrix of Hadamard gate. 1 over under root 2 ket 0, 1 over under root 2 ket 1. Yes? So we didn't think about it. We just referred to the matrix and we wrote the column matrix. Okay? Now, next. So this S gate gets an input of this qubit. Yes? So we write this qubit. We have this S gate. Now we have to apply this S gate on this. Right? So we'll apply it in pieces. We'll see that what happens to ket 0 when S is applied. So we'll replace ket 0 with that qubit value plus then we'll see what happens to ket 1 when an S gate is applied. And we'll substitute the value here. And how will we get the values? So when S gate is applied, ket 0 remains ket 0 and ket 1 becomes iota ket 1. Yes? So now if you can see, when an S gate is applied, the scalar values remain as it is. 1 over under root 2, ket 0 remains ket 0 plus ket 1 becomes iota ket 1. Yes? You don't have to think what happens to a ket plus. You just have to know what should happen to ket 0 and ket 1. With me? Take a minute to absorb it because next sequence you're going to solve it for me and then I'll flip the slide. So in the next circuit, the next step, what happens is that this is the input This is the input, and what gate is applied to it? Hadamard, right? So write the gate line Hadamard, and while we have a break for prayer, please resolve that.
Taking a little bit time because sure.
It's a good thing that all of you are following, and I hope our online participants are also following. So what happens is that this was the question that was given to you. So please verify your answers, because ket 0 was replaced by ket plus, and ket 1 was replaced by ket minus, and then I kind of sort of simplified it, and this is the simplified answer. So please excuse my writing and please verify your answer. And following the same, do we end here, or do we have another step remaining? Apply T-gate. So the same process would be with the T-gate. So what happens is that we have this matrix that you have already calculated. Then we'll apply T-gate. Applying T-gate means that ket 0 is transitioned to to whatever it says, and the ket 0 remains ket 0 as it is. So in Z phase gate and in phase gate, S gate and T gate, this ket 0 is never changed, right? So ket 0 comes out as it is, and ket 1 is replaced by the updated value, and then we simplify it and we get the final answer. Okay? So now just to summarize, today the first important part of what we're doing today is that given you have a circuit, you need to solve it through two methods. One is the detailed method of matrix multiplication that you'll do for 2 or 3 circuits. After that, you'll start skipping it because it's a lengthy process, but you have to know it, right? And the second, I call it the intuitive method, right? It's a tensor product. You solve it by individual effects on the individual gates. And once you get hold of it, trust me, I'll give you the supercomputing, super dense coding circuit, and you'll solve it by yourself. Okay? So I think we should have a break and then we'll reconvene. Thank you.
Any questions? Just giving the answer.
Just wanted to check how we know which state is to use supply. Well, Ayasa, as I defined, you have to multiply the H, S, H, and T. So this is the reverse order. So we have to take the H matrix, then we multiply with S, and then the answer is multiplied with H, and then the answer is multiplied again with T to get the bigger unitary matrix that we can solve. Voice is low. Please ask the speaker to move the mic closer. Thank you so much, Fatima. I'm sorry, I might have drifted away from the mic. I'll keep that in mind. So please share the link here as in the middle of somewhere. Okay. Any question? The bigger unitary matrix is also called a composite gate. Yes. It's reversible and it has all the properties. It's a unitary gate. Okay, now we can have a break, probably. And for the online users, I really hope that you're solving the questions by yourself. And we're going to have a lot of questions after the break as well. Thank you. But Umeed hai that now you know how the presentation would work. That means that you'll have a circuit and you'll have to solve it. The rules are the same. It's a bottom-up approach. The qubits are initialized as 0. There are two methods to solve it, an intuitive method and a mathematical method. Mathematical method means कि आप सबको combine करके एक unitary matrix बना दें और उससे multiply कर दें. And the intuitive method is कि आप step by step उसको चलते जाएं. ठीक हो गया? We've just wait about for 3 minutes, but till then, till everyone comes, this is your circuit. You have two qubits, Q1 and Q0. There are two methods to solve it. One is an intuitive method and other is a mathematical method. So although the solution is there, I would like to request you कि आप अपने papers, sorry, there are international students with us. So I would like to request you all to please solve that on your papers, both intuitively and mathematically. Although there is one challenge in this. Can someone tell me what the challenge is? Yes? Yes. So you've discussed tensor product in past 2 days? No? Okay. In some simple terms, do you see a problem here? Intuitively, it's good to solve, yes? So 0, 0 here, the answer would be what? चलो पहले intuitively solve करो. Solve it intuitively and then we'll come to the matrix multiplication problem, but it has a problem in that, okay? So solve it intuitively. Think about what happens to qubit 1, what happens to qubit 0, and then write the answers. And then tell me what the final answer is. Responding to ask and who should be paying?
Why did
Yes, time है. लेकिन डांस पे तो वो मेरे साथ भी थे. यहाँ बैठे हुए थे डॉक्टर हमाद. ठीक है. उनसे आप एक दफा पूछ सकते हैं? पूछाते हैं फोन पे रिप्लाई नहीं कर रहे सर. हाँ. वो आ गए. I was just trying to ask if Okay, Ji. So the next circuit that we have is a 2-qubit circuit. So a 2-qubit circuit in which we have 2 transitions in each qubit on the qubits. Now there were 2 methods to solve it. One is an intuitive method and one is a mathematical method. So first I would deliberately solve by the intuitive method, and then I'll come back to the mathematical method, and there's a challenge associated to it. We'll discuss that. So if we consider qubit 1 transition, so qubit 1 transition is by default ket 0. We apply X gate, we get ket 1. In qubit 0, we had ket 0. Hadamard, we get the answer this. Yes? Now, what is the approach of reading the qubits in Qiskit? Bottom up or top down? Bottom up or top down? Bottom up, right? So here we have ket 1, and here we have 0 and 1 with equal probability, right? So the final answer would be 1 over under root 2 ket 1 0 plus 1 over under root 2 ket 1 1. Why I'm reading it like that? Because Qiskit actually reads the circuits in a bottom-up approach. So the answer would be, what would be the answer? So is how we write it? We write it like that. We have ket 0 0. I need your attention here. So we have ket 0 0 and we apply x tensored with h. That means that on the first qubit, x will be applied. On the second qubit, h will be applied, right? So on the first qubit, 0 transitions to 1, and the second qubit transitions to ket plus. Now we just have to solve it. How we're going to solve it? 1 over under root 2, ket 1 0. 1 over under root 2, ket 1 1. So this is the way how we solve it. And then the final answer that we get is the probability, equal probability to land as a 1 0 or a 1 1. So if you draw it, sorry, no, back. So this is the answer that we get a 50-50 probability of 0 0 and 1 1. So for 1 0 and 1 1. Yes? The important thing, very important thing to note here is, in the last circuit, there was only 1 qubit. So it was very easy to solve for you, okay? Now we have 2 qubits. So we write it as a 2 qubit system, starting from 0 0 and then transitioning each position based on the position of the gates. So write it down, make an important star, that if it's a 2 qubit system, we'll write it in a composite form, and then based on the order and the gate application, we'll apply the gates one by one. So that's the key takeaway here, okay? Now, coming back towards this problem, that was the intuitive solution. Now, while we solve it mathematically, we have to solve it collectively. The input would be 0 0, right? That will be defined by a 4 cross 1 matrix. Yes? Yes? So we need to have a 4 cross 4 matrix. So this should be resolved into a 4 cross 4 matrix so that we can multiply a 4 cross 1 matrix with it. Yes? Yes? No? Right. So we have an H gate that is a 2 cross 2 matrix. We have a X gate that is a 2 cross 2 matrix, right? But we have to make a composite big circuit that can be applied on both the qubits simultaneously, right? So what would we do? We would combine these two operators using tensor product. So this is one mathematical concept that you should know, tensor product. So tensor product, what does it does is, simply put, it actually combines the smaller circuit into a bigger circuit, okay? So you need to see it mathematically, being very simple. One most important thing, we're using the bottom-up approach, right? So if you're using the bottom-up approach, it would be X tensor H, right? So it's not commutative. We cannot write H tensor X. We're working with Qiskit. The answers are from the bottom up approach. So we have to read it from the bottom up. So it is X tensor H. That is important, right? So how we solve it, X tensor H? I hope it's very simple. So we multiply this whole vector with each of the component, treating it as a scalar, okay? So this whole vector, when multiplied with 0, it gives you 4 zeros. When multiplied with 1, it gives you the matrix itself. Simply here, similarly here. And 1 over under root 2 is the overall scalar value which is multiplied here, okay? So, so there are two important things in this slide. Number one, in order to make a smaller 1 qubit system into a 2 qubit system, we need tensor product, right? The second important thing is that tensor product, while working with the Qiskit circuit, we have to use a bottom-up approach, right? So bottom-up approach means that X tensor X is not equal to X H tensor X. So we are working with X tensor H because we are working in the bottom-up approach. The third important thing is how to take tensor. Take first matrix, each of the component, treat it as a scalar, and then multiply each vector with one of the components, and you get a 4 cross 4 matrix. Now things are very easy. Now we have ket 0 0, and we have a 4 ket 0 0 is represented by this. Yes, everyone agrees. So we multiply it with this whole circuit that we calculated earlier, and we get the answer. Now, can you verify this answer to be the same as you calculated intuitively? So the answer that we calculated earlier was 1 over under root 2, 1, 0 and 1, 1. Yes? And this is 1 over under root 2, 1 over under root 2, 1, 0 and 1, 1. Yes? Okay, so the two new things that we studied or we learned about in this lecture, in this circuit. Number one, we need tensor products to actually combine multiple single qubit systems. We need tensor products to combine multiple single or double qubit systems. Yes? Number two, intuitively, when we solve something, we solve things collectively. We don't do it like this. This is a naive kind of an approach. If we have 2 qubit system, we take input 0, 0, and then we apply the gates on the appropriate position. Since Hx was applied on the most significant side, that is why it was converted into 1, and H was applied to the least significant side, that is why it was converted into a plus. So these are the three takeaways. Multi-qubit system, tensor product, and in the intuitive manner, we actually take the whole system, not the individual qubits. And the bottom-up approach is very important. Everyone agreed? Now, it's a quiz time. So, you have the login pages with you. I'll give you a time. No. I'll give you a time. Don't start. Okay. So now take some time. You have this circuit. Like it, solve it mathematically, solve it intuitively. Pro tip, intuitively an easier version to solve. Solve it on a paper and then I'll open the quiz. So you have about 2 minutes to solve it and then I'll open the quiz time. So starting with, we have 0, 0, and then the gate that would be applied would be X tensored with Z. Anyone wants to apply Z tensor with X? Anyone who wants to apply Z tensor with X? Why? Why? No. Yes, it's not commutative and we're working with the bottom-up approach. Yes? Okay. Any question? Okay, solve it. Okay, so I hope you have solved it. Can I open the quiz? No? Okay. So anyone having any difficulty, please ask me or ask Varda. She's here to help. So 0 0 के ऊपर यहाँ क्या आएगा, यहाँ क्या आएगा? Identity means nothing happens. 0 remains 0, 1 remains 1. In the second phase, we have पहले हम ये करेंगे. The answer of this expression goes as an input to the next expression. Yes? Whether you're requested to open the quiz now. So you have about 1 minute to solve the quiz.
Remain active.
Open the Metimeter page. You'll get the question, and the question is to give the answer of this too. Have you solved it? Okay. This link will remain active till tomorrow. We have a lot of questions, and at the end of tomorrow, I'll tell you who's the winner. No one's active? So we'll wait about for 1 minute and we'll move forward. Let me know when 1 minute is down. Timer's off?
Timer's on.
Okay. So those who are online, please, solve this and give the answer. The quiz actually asks you what the answer is. Okay, is 1 minute end? Okay. Okay, while everyone, so let's come to the answer. So is this the answer that you've got? Equal probability of 1 0 and 1 1? And everyone understands how? Everyone understands how? Okay, great. So if no one, just for my reiteration, 0 0, first 0 was translated into 1 and Z translated 0 into 0 itself. Then in identity, 1 remains 1 and Hadamard remains ket plus, and then ket plus is expanded to give the final answer. Okay? And now if you want to solve it mathematically, you can do it by yourself. So we actually calculate Z tensor H first and then I tensor H. Now my question is that this is a 4 cross 4 matrix, this is a 4 cross 4 matrix. So if I want to make the expression of matrix multiplication, should I do it? How should I write it? I mean, if I'm reading it from here, I'm going to write it. Yes. So it will be I tensored with H multiplied by X tensored with Z. Right? So this is what I'm talking about. So Z tensor with X tensor with Z is first, and then I tensor with H. So since matrix multiplication is not commutative, you have to be very careful about the order. Okay? So now we solve this question in different two manners. One is an intuitive manner, one is a matrix multiplication. And matrix multiplication, we had two concepts, tensor product and the order of the multiplication. With me? Good. Now, this is an interesting gate. it has two representations, right? First approach is a bottom-up approach and second is top-down approach. Okay, listen to me very carefully. Whenever you have a matrix, first column gives you the output of the first input. That means this is the output of 0, 0. This is the output of 0, 1. This is the output of 1, 0. And this is output of 1, 1. Okay? Now this is written in a top-down approach. Top-down means that the most significant bit is the top one. Okay? So 0, 0, input 0, 0 would remain output 0, 0. So this matrix will remain like that. Okay? Then 0, 1 would remain 0, 1. Still same. This is 0, 0, 0, 1, 1, 0, 1, 1. Okay? For 1, 0, what would happen? 1, 0, what would happen? 1, 1? That means 0, 0, 0, 1. This should be the output. Right? And for 1, 1, what should be the output? 1, 0. So this is the output. Yes? Everyone agrees? Now, this is also a C0 matrix, but this is with respect to a bottom-up approach. Right? That means in this setup, 0, 0 means that the most significant bit is the target bit and the least significant is the control bit. Okay? So 0, 0 means the output would be 0, 0. Here it is. Okay? 0, 1. What would be the output? 1, 1. Can you verify the output? Yes? 1, 0. Output remain 1, 0. So yes. And 1, 1. 0, 1. Here's the output. Okay? So my question is, quiz is open. Just check it and give the answer. The question is that for bottom-up approach, while solving the Qiskit circuits, which circuit should I use? Which matrix should I use? The first one or the second one? In Qiskit, while solving the mathematical expressions, you have two different matrices for C0. Which matrix should I use? Top to bottom? Bottom to top. Yes? Because in Qiskit, whenever we solve the thing, we solve it from bottom to top. So this is the matrix. Write it down. Whenever we have C0 in our circuits, we'll replace it with that matrix. So this was the reason why the matrix was not given earlier for C0. Okay? With me? Solve this. Solve this intuitively. So the main key takeaway of today's all this workshop is that you should be able to solve a circuit. That's it. So solve it intuitively. We have the input 0, 0. In first stage, first qubit, nothing happens to it. On the second qubit, 0 converted into ket plus. Write it down. In the next step, what happens? The most significant bit is the target bit and the least significant bit is control bit because of a bottom-up approach. And we have C0. And we have to convert the input qubit using the bottom-up approach on C0. Okay? Solve it and give me the answer. Anyone who's clueless? Whether just have a round around. If someone needs any help. So, okay, I'm skipping the quiz now because I have less time available. So I had 0, 0, and I had, because I had nothing here, so I'll put an identity here, okay? So I had identity tensored with H. Yes? So identity means nothing happens to get 0, and H means that get 0 is converted into get plus. Yes? So now we combine it and we have 1 over under root 2, 0, 0 and 1 plus 0, 1. Yes? Okay. Now we apply C naught here, and since it's a bottom up approach, the most significant bit is the target bit and the least significant is the control bit. Okay? So 0, 0 will translate into what? 0, 0 again? Good. And 0, 1 will translate into 1, 1 because the target bit is 1 and control bit is 0, so 0 is flipped to 1. Yes? So the answer to this question is equal probability of 0, 0 and 1, 1. And can you identify this circuit? Is this a known circuit? Have you seen this circuit anywhere else? Yes? It creates a bell state. So it's a 5 plus bell state. Yes? You might have seen it earlier. Yes? Okay. So for your own interest, I've solved the matrix part of the solution. The solution is there. You want to solve it, you can solve it at your home because I don't want to waste much of your time here because this is the time that requires practice. At the beginner level, you definitely use the matrix multiplication, but after some time you stop using it. Okay? Okay. So this is the matrix that appears after you simplify everything. So you have all the answers with you, so you can easily cross-check your answers. Okay, and one of the small home assignment, if you want to do, is that you people have solved this bell state for me. Now, intuitively, you're required to solve all these other bell states. So the spaces which are left here, you can consider it as an identity. So we'll start as 0, 0. Next is 1, 0. Then next is 1 ket plus, and then the conversion. Okay? So practice it so you can do it well. Okay? Next is, these are some big circuits. Again, I would like to request you to solve all these circuits. And if you want to discuss anything with me, you can discuss this. And I'll also provide the handwritten solutions to these, both the intuitive and the mathematical. So if you want to test by yourself, you'll get the solution to these all questions and you're requested to solve. And if you have any question, you can come back to me tomorrow. Okay? Whether we'll provide them a solution today? Okay, good. So you get the solution to all these questions, but you have to solve these. So there are total 5 circuits. Okay? And you have to solve it both intuitively and mathematically. So having said that, we have about 3 till 3:30, and the next agenda for today's presentation is superdense coding. Now, there are 3 important things that I want to discuss regarding superdense coding. First, what superdense coding is. Second, what is the circuit of superdense coding? Third, how to solve it. So how solving it part is sorted, I hope, because you're going to solve it for me. So we'll discuss what superdense coding is and how does the circuit look like. So anyone has an idea what superdense coding does? Yes? Okay. Can you be a little bit more precise? You're absolutely right. So if I simplify the problem, it is used to transmit 2 classical bits using 1 qubit and at the expense of 1 e-bit, या 1 bell state or 1 entangled bit. Okay, so it is used to transmit 2 classical bits through 1 qubit at the expense of 1 entangled state. at the expense of 1 EBIT. Okay? With me? So the simple statement is that it is the efficient way of transmitting information given we have a good quantum channel, and through 1 qubit we are able to send 2 values. The second thing is how the circuit looks like. So you have to understand that this is the information channel where we want to communicate. Okay? So suppose we want to transmit 1 1. So the 2 bits that can be transmitted. So D is equal to 1 and C is equal to 1, right? So if we want to transmit C and D through 1 quantum bit at the expense of 1 E bit. Make sense? Okay, now this circuit is a conditional circuit. That means that if the value of D is 1, in that case Z gate is implemented, otherwise not. And if the value of C is 1, only in that case X is implemented, otherwise not. Okay? So if we want to transmit 1 1, this is the whole circuit. If we want to transmit 0 1, that means it won't have a Z gate, it will only have an X gate. Yes? And if we want to transmit 1 0, what would happen? Let's do it from the top. You have to send classical information through quantum channel. You can transmit 2 classical bits through 1 quantum channel. Okay? So in 2 classical bits, how many combinations are possible? 4, 0 0, 0 1, 1 0, 1 1. Yes? If we want to transmit 0 0, then the circuit would simplify itself by not including these 2 gates. Okay? If we want to transmit 0 1, then this gate won't be here, only this gate would be here. If we want to transmit 1 0, then this gate would be here, but this gate won't be here. And if we want to transmit 1 1, then these 2 gates would be here. Okay? So every time with the information that needs to be sent, the circuit is updated. Okay? So we are going to study the maximum circuit, and then you can solve the circuits which are simpler ones. So which information are we going to transfer? Which is the biggest circuit? 1 1. Yes? So this is the circuit for 1 1. Okay? Now we are going to solve it layer by layer. Okay? So the input is 5 plus. 5 plus opens up as? What's the value of 5 plus? This is the value of 5 plus. Okay? Again, we're following which approach? Bottom up or top down? Bottom up. That means that 0 0, we read it from here. Okay? So on the input, we have 0 0 plus 1 1 by under root 2. Everyone with me? Now I need your participation in that. Okay? So next is this circuit in which we apply a Z gate. So actually what we are doing, we're applying a Z gate or we're applying I tensor Z. What are we applying? A Z gate or I tensor Z? I tensor Z. So what happens is, grab your paper pen and write it down that the input was this, that was the 5 plus state. We applied I tensor Z. So the 0 qubits would remain then as it is. And because of Z, this 0 will remain same, but this 1 will convert into minus ket 1. Everyone following? So if everyone's okay with that, write this down and solve the next step for me. What would be the next step? Simple X gate or I tensor X gate? To what? To the output of this? So the next line you write this, You make an arrow like that. You write I tensor X and then you solve it and give me the answer. Everyone who doesn't have an idea? Anyone who doesn't have an idea what's going on? If I can help them? How many of you have got the answer? Good, great. One student? Anyone else who has got the answer? Good. Two students? Anyone else? Now I'll show you the answer. Done? Everyone done? Should I show the answer? Okay. Please match your answer. X was simple. X was simple. In identity, 0 and 1 remain same, but here the 0 and 1 gets flipped. So this becomes 1 and this becomes 0 and the minus same sign remains there. Yes? Okay, Ji. So now this is the state that we need to hold on to and we'll move to the next layer. Okay, so this is the state where we want to hold on to. Everyone has that state? Okay, so the next step is this C NOT gate. So although the answer is here, but I would like to request you all to solve this, remembering it's a bottom-up approach. So the most significant bit is the target bit and the least significant bit is the control bit. Yes, you have the answer here, but please try to solve it by yourself. The previous answer is now applied to C NOT gate. The previous answer is now applied to C NOT gate because we're solving it in continuity. You've got the answer? The answer matches? Everyone with me? So what's the next step? H gate? Only H gate or I tensor H? Shouldn't it be H tensor I? I tensor H. Yes? Why? Because we were working on the bottom of approach. Now the previous answer, pick that previous answer, apply I tensor H and get the answer. Give me the answer. What should be the answer? We were trying to communicate 1, 1. Yes? So what should be the answer? सुबह आपको बताना चाह रही थी लेकिन मेरे पास टाइम नहीं था प्रोटोकॉल आज नहीं कर रही आज कैसे होगा और मैं तो प्रोटोकॉल फॉलो करके लाए Do you think we can cover it till 3:30 or maybe 4? No, 4 तक तो time. 4 तक time खत्म करें 3:30 तक. So should I give an overview of the efficient protocol and then you can give the overview and then you can quit tomorrow. Yeah. Right. And yeah. The rest of it is yes. I would repeat the session yesterday. जब मैंने कल कराया वो simple gates थे. ठीक है और आपने कंपाइलर्स कैसे कॉल ऑन करने का आदत से आपने मुझसे कहेंगे कि नहीं कहती कि आपके सुपर डेंस कोडिंग का सर्किट चलाने उससे इन बच्चों को नहीं इन्हें मैं ना जो सेशंस करा रही हूँ तो मुझे पहले नहीं आता कि उसके मैं को आ गया तो फिर मैंने पहले दिन से सेटअप इनिशियलाइज करना सिखाया मेरे गेट लगाना सिखाया Do we have the answer? What is the answer? Minus 1 1 आ रहा है. So what does that mean in terms of probability? 100% probability of 1 1. And what was the aim of the super dense coding? Sending 1 1 to the other end, right? So minus is the global phase, that does not matter. So what we have is that when we apply I tensor H, 1 remains 1, 1 remains 1, and 1 becomes get minus. Here 1 remains 1 and 0 becomes get plus. And when you solve it, it's a little bit of a bigger maths, and then you get the answer of minus 1 1. Minus is a global phase, that does not matter. And this gives the 100% probability to land as a 1 1. Yes? So what was the purpose of super dense coding? To communicate two classical bits which we selected to be 1 1, and to get them on the other end using 1 qubit and at the expense of 1 e-bit. Yes? Make sense? Okay. So measurement probability is 100%. So now what I want you to do is, I'll show you the circuit, but I want you to resolve the circuit, the whole circuit, and now I want you to transfer 1 0. The value of D is 1 and value of C is 0. So I'll show you the whole circuit. Here is the whole circuit. I should show you the bigger picture. I think that's way. So 1 0 means that the value of D is 1 and the value of C is 0. That means that there won't be any X gate. The circuit will only comprise of Z gate, followed by C naught gate, followed by H gate, and the input would be 5 plus. Okay? Everyone got my question? Everyone understood the question? So I think this would be the last thing that I would like you to cover today. And after that, Ma'am Mariam and I would give you slide demos of the quantum circuit so that you can actually see the outputs, what you have solved today. And then a small demo of super dense coding and a small hands-on introduction to teleportation. Tomorrow, we shall start with teleportation and then we'll discuss phase oracles. Okay? But the important thing here is, today the key takeaway here is that now any circuit that you have, you should be able to solve it, either intuitively or mathematically. Would you please have a round if anyone having any difficulty? So now the last task for today is that you need to transfer 1 0 from one end to another end. That means that you keep the Z gate as it is, you omit the X gate, and then you resolve the circuit. While they're doing that, can you show me the comments? The online. Okay. Congratulations, Neuroland, for the summer school selection. Yes, I guess certificates will be provided at the end of workshop. Please go up. Okay. I think फिर नीचे आ जाए. Just wanted to see if there's any other question left. Okay. So I hope my online participants are also working on the question that I've given. Please show me the new message. Is a single state and beta 1 1 same? I'm sorry, Seth, I can't make sense of your question. If you can be a little bit more elaborate. Okay, I think we can wait so you can remove the comments.
ये तो 1 1 ही आया 1 0 वाला चाहिए सॉल्व करने हाँ ना पाया चले करें यस आया मैंने बस वो कलेक्ट करना है इट्स ओके Can you get the answer of 1 0? Okay, so we started with 0 रिकॉर्डेड ब्रीफिंग्स का कैसे मिलेंगे
If I can have access to that. Thank you. I can just show them. मुझे सिर्फ IBM composer चाहिए. मैम ये वाली स्क्रीन वहां कैसे आएगी? शेयर कर. Okay जी. So while you're doing that, Varda, so वो स्टूडेंट उनको हेल्प चाहिए नहीं पीछे अच्छा done. Okay जी, while you're doing that, the last bit that I want to cover, Ma'am Mariam last time introduced you with Qiskit and she introduced you with Python coding. So another alternative that is for very small circuits that is simple to use, but the only limitation is that it is limited to 4 qubits if you're using it without sign-in, and it is limited to maximum 6 qubits if you're using with the sign-in. But since we're doing super dense coding, it shouldn't be that of a problem. So this should be the kind of layout that you should get if you have scanned QR1 code. Okay. So this is an IBM code composer. This panel here consists of all the gates, H gate, X gate, C naught gate, so that you can drag and drop any gate here. So that the answer is, this is the plane where you get the outputs and you want to see that. So this is the simplest method. And Dr. Hamad was very rightly saying about the assembly language. So the good thing about this circuit is that while you drag and drop the circuits here, the assembly language code is being developed on the other side automatically. So now what you're going to do is that we're going to use super dense coding and we want to solve super dense coding. So for the super dense coding, we wanted 5 plus as an input, right? So the 5 plus circuit is something like that. We have already solved it. Yes? Yes? Okay. And we are applying some of the barriers here so that we can start from here. So this actually, because the initial inputs were 0, 0, and we wanted 5 plus as an input, so we had to do something with the circuit to get 5 plus as an input. So this is the circuit to get 5 plus. Okay, and this is the Bell state circuit that we have already solved, the first Bell state circuit that we have solved. Okay, so now from this barrier onwards, I'm going to make this circuit that is for super dense coding, and that will communicate two values, two classical values from entity A, say Alice, to entity B, say Bob, at the expense of one E-bit. Now we're assuming that these entangled qubits are positioned at different places. One qubit is at Alice's side and one is at the Bob side. Okay? So first we have to apply Z gate. Next we have to apply X gate. What was the next gate? What was the next gate? Okay. So if we, without applying measurement, we can get the answer. But as you can see, that if I get the answer and I want, because there are only two qubits, so the answers can be maximum four possible values. So you can see that if we do this, the answer would be 1, 1. Yes? And if I omit this, so the answer would be, if I omit this, what should be the answer? If the value of D is 0, if the value of D is 0 and value of C is 1, so we have to omit this gate? Yes? Yes? The answer should be 0, 1. So let's see if I delete this, do I get the answer of 0, 1 or not? 1, 0. Why? Because we're using the bottom-up approach. Okay? So this takes a little bit of a time, but I can share you this code file with you, but this is a simple circuit. I would really recommend you all to, use this drag and drop model. It does not need any installation. It's one QR scan away. So you have it on your own systems, drag and drop the circuits, and the practice circuits that I've given you. Solve those circuits, draw them on the composer, and then see the answer for yourself. That would help you a lot. Okay? That's all from my side. So super dense coding hands-on is done. Now, Ma'am Mariam would elaborate teleportation. She'll show you the circuit and then she'll show you the coding. Now, I'm very hopeful that you can try to solve the teleportation circuit. Otherwise, we'll do it tomorrow. Okay? Thank you so much. It was very nice teaching you. See you tomorrow. I'll be here.
We should have a break of 10 minutes before starting it. So after 10 minutes, we're gonna see the teleportation circuit for a bit. But before that, I'm gonna repeat the session that I did yesterday. How to use single gates. We already know that how can we call the gates, how can we use the air simulator or chasm simulator if we want in Jupyter Notebook. And then I'm gonna explain the circuit a bit. But the important thing is I won't go into details since you're not familiar with the teleportation protocol right now. But tomorrow when you're gonna learn from Dr. Madiha, then you're gonna understand it better. And I'm gonna share this demo in the Discord group that I made. So you can run this code and see that what is happening if you're doing. All right. before I start, I want to ask that are you guys enjoying or liking it, or is it a fascinating thing for you guys that you're gonna continue over for your MS or probably PhD? Yes, that's good. Okay. So I'm gonna revise first two demos that I have shared in Discord group that we learned, and today I'm gonna first give you an overview of the teleportation protocol. What is that? How does it work? Then a bit of demo that I created, but since you guys are not familiar with the teleportation protocol and Dr. Madiha would explain, the original plan was that Dr. Madiha had to explain this today, so I would have been covering this demo, right? But since you guys learned about the super dense coding, so I'm going to explain this teleportation protocol myself, a little demo, and then tomorrow when you're going to learn about the teleportation protocol in detail, then you can understand my circuit a little bit better, okay? So first things first, and we learned that how can we from the top, we learned that we have Jupyter Notebook, we have Python programming language, and we have a QSkit library that has predefined functions as quantum circuits, as air simulators that we can use for simulating our circuits, our quantum circuits. It's going to the quantum simulator, and also you can use API key token to send your code to a quantum computer that IBM have. This is also a possibility. First, you use the quantum simulator, and then you think that if your code needs to be run on the hardware, on the real hardware, then you can also do that by sitting here. You can get the API token key, and then you can send your code to there, and they're going to run on the quantum computers. First thing. The things that we learned from the start is we know that we're going to use the Python program language for the QSkit, and we're going to call some basic classes from that library that has quantum circuits, and we have used poly-X gate, poly-Y gate, poly-Z gate, and I told you that when we start, the predefined thing for the circuit to start is that we have a 0 state to start. So if you have initialized one qubit as quantum circuit 1, then it has a 0 state. And if you want to start with some other state, then you have to use an initial state function and tell your initial state to be 1 or in plus or minus eigenbasis. That was 0 plus 1 and 0 minus 1. This was the whole overview of the first two demo sessions. Yesterday, I explained that a little bit about the superposition circuit. So it was superposition circuit as well as how to generate a Bell state. So you guys all know that Bell state is an entangled state. And what I mean by entangled state is a simple definition is that you cannot write that state into a tensor product, right? This is not possible because one state is related to the other state. So this was the circuit that I explained yesterday, that how can you generate a Bell state. So the first line, I'm going to go with the first line. So the first line is quantum circuit 2 and 2. So now in the start, I told you in the first demo, we were writing quantum circuit 1. That was initializing 1 qubit. But as you go and you are getting, as you go, you're getting professional in programming as well. So now the good rule of thumb is basically to use classical and quantum registers. So can you change the quantum bits every now and then? So here I initialize the quantum registers, and now I'm using these two registers in the whole program, right? So these are the quantum and classical registers for 1 bit, for 2 bits, whatever you want to decide. So here I'm basically having 2 quantum bits and 2 classical bits, right? And then what I'm doing is basically this is I'm applying a Hadamard gate on 1 qubit that is 0 index, right? So if we have 2 qubits start with a 0 and 1 and we're applying Hadamard to the 0, and now what state would be having is equal to 0 plus 1 into 0, right? Divided by under root 2 as well, right? So now the original product can be written as 0, 0 and 1, 0, right? So the state now we have is 0, 0, 1, 0. The next what we are doing, we are using a control NOT gate in which we are using first bit as a control bit and the second bit as a controlled bit or a target bit, right? So if the first bit is 0, it would not change the state of the second bit, but if the first state is 1, then the target bit or the controlled bit is flipped. It would get to the, if it's 1, if it's 1, then 0, if it's 0, it's 1, right? So now we have a state as 0, 0, 1, 0. In 0, 0 span, we have a control bit of 0. So the target bit 0 would remain the same. But if we go towards the second state, that is 1, 0, we have a target bit of 1. So the second bit would be 0 to 1, right? Now we have created a Bell state that is 0, 0 plus 1, 1 divided by square root by 2. That is probability. We are not so much focusing on the probabilities now, but this is, you have to keep in mind, right? For my curiosity and for your curiosity to do as well, I always measure and also draw my circuit because I want to see what gates I'm using. And also Dr. Madhiya explained the flow of the qubits and how the gates are you're adding. So this would be good practice to see that you're using different circuits, gates to how you're like making your circuit, right? One important thing that I explained yesterday, we have two kind of simulators in IBM. One is air simulator and second is Kaizen simulator. In this program, I'm using both of the simulators. I'm calling both simulators here. The difference that I want to explain in a very layman terms that you can understand is, we all know that if you measure a quantum state, it collapses, right? We collapse in superposition and we only know the definite state when we use any kind of measurement operator, right? So if you want to measure the quantum state without measurement operator, the exact quantum state that has not been collapsed yet, you would use air simulator, right? So this is the simulator when you want to use the exact quantum state, but this is not possible in quantum hardware. Because in quantum hardware, we always have to use some kind of measurement operator or measurement tool that can be photon detectors or anything. These are all measurement operators. For that, we use a Kaizen simulator, which is basically a replica of exact quantum hardware, which gives the probability counts that the 1 is occurring for this many times or 0 is occurring for this many times, right? Then we also using from time to time the words shots and counts. Those are very important words when you're coming to programming, Q-skit programming, quantum programming. So we all know in a classical domain, we have one input and one output. It's not reversible, right? So we have one output. But in quantum domain, we have certain input, but the output is in probabilities, right? To get accurate probabilities, we have to simulate our circuit again and again. So if you simulate your circuit one time, it's called one shot, right? So the maximum shots IBM can give you is 1024 shots, and it would give you a relatively good probability of occurring of 0 and 1, right? So by now, I only demonstrated because I want to get you guys familiar with the Q-skit first, and how can we use single bit gates, right, before going to the protocols or algorithms. Today, however, we're going to discuss a protocol, but I would be a little slow with that because you guys are not familiar with this protocol. First, we're going to understand the protocol and the basic steps, what is happening. So we're having the only basic gates in this protocol, that is Hadamard gate and control NOT gate. This is the only gates we're using for the teleportation protocol. Now, what is teleportation protocol? It's a magical protocol in quantum, which is used to transfer one state to another state by using an entangled pair, right? So in our program, we're going to using the entangled pair that would be Bell pair. Bell pair, we know it's entangled state, and we would initialize some state that belongs to Alice. And after certain manipulations, we would see that Bob has that unknown state. But there's a twist in that. In this, we are also using some kind of classical communication as well. We're going to see that. I'm going to be, you can stop me if you don't understand, but I'm going to be explaining in very layman terms first, what is teleportation protocol. So first thing first, we have this psi alpha 0 plus beta 1 as a state that we want to transfer from Alice to Bob. Now this state belongs to Alice, and we want that we can send this state to Bob after certain quantum operations. We're going to see. The first step is basically Bob shared an entangled pair, right? Alice and Bob, they have an entangled pair. So we're going to be using the Bell pair as the shared pair between the Alice and Bob. So this B00, that is 0011, it's a Bell pair, and this AB is telling me that one bit of Bell pair belongs to Alice and the one bit belongs to Bob. Now they're connected in a way that they have an entangled pair. The second thing is, the first state would be the psi, the unknown state that we want to transfer, and the Bell pair tensor product. And Alice applies a control NOT gate on her qubits, right? On her qubits, not on Bob qubits. That's important. So if you write this state, we can write this state as this, right? This is the unknown state that we wanted to transfer, and this is the Bell state. Now, if we do the tensor product, then we get these four terms, right? And the first two qubits, that belongs to Alice, because this is Alice, right? Here we have this bit belong to Alice, and here we have this bit belong to Alice, right? So in this term, the first two qubits belong to Alice, and Alice is going to apply the control NOT gate. And we know the functionality of control NOT gate is basically, if the Alice qubit is 0, then the target bit would remain the same, right? But if the Alice qubit is 1, the target qubit would be 1. It would be flipped, right? So here in these two terms, we're going to be seeing some flipping. This is 1, it would make it 1. This is 1, it would make it 0. Now, I explained the control NOT gate, and I explained in detail that we can apply the control NOT gate. And you see, after that, we reach to this state after the control NOT gate, right? Now, what we want to do is, Alice wants to apply all operations are applied through the party of Alice, not Bob. But in the end, you would see that Bob would get the unknown state that that belonged to Alice in the first place, right? So now, if we do some kind of rearranging, right? First, I'm going to explain that what is Hadamard gate. You guys already know by now that Hadamard gate creates a superposition, equal probability. And if we take 0 from common from here, the Alice bit, right? And 1 from here, the one thing you can do to simplify is basically use the transcripts, where subscripts you're using Alice and Bob, then that you know that this bit belongs to Alice or Bob, right? Now, in this 0, we're going to apply a Hadamard gate. And in this one, we're going to apply the Hadamard gate. So now, by applying Hadamard gate on 0, we have 0 plus 1. By applying Hadamard gate on 1, we get 0 minus 1. Exactly. Right? Now, you guys have a simple terms, and what you're going to do is basically do the multiplication, right? And then we get all these pairs, right? You can take the common, it's relatively easy. And if you guys cannot do, then I would do this calculation with you guys, but it's relatively simple. Now we can see the important part here to see is, now, if you use the subscripts, you would see that this 0, 0 belongs to Alice, and this 0 and 1 belongs to Bob. Now we have 4 terms, 1, 2, 3, 4. This is written there, right? We have 4 terms in which 0, 0, 0, 1, 1, 0, 1, 1, this belongs to Alice. And this term 0 plus 1, 1 plus 0, 0 minus 1, 1 minus 1. This belongs to Bob, right? So now here comes the part that we have to convey our Bob, the other party, that we are doing some kind of measurement, and you have to use this measurement operator, right? If we use 0, 0 measurement operator, what state would we get? This one, 0, 0 in our product with 0, 0 would give us 1. We would get this state, and this state belongs to Bob. So I think this is the same unknown state that we wanted to transfer, right? So this was the state that we made, and Alice had is first this state, and now after certain manipulations, Bob has this state, right? But now there's a twist here, because not every time we are using the measurement operator 0, 0. Sometimes we're going to use the measurement operator 0, 1. If we're using a 0, 1 measurement operator, then the state is not the same that we were transferring in the first place, but a little bit difference. If you guys think a little bit and we use NOT gate here, this will convert 1 into 0. This is convert 0 into 1. Then this would become the same unknown state, but Bob is going to apply one extra gate on his side to get the exact state. Now, Alice has to inform Bob over a telephone that you have to apply this gate. I have this bits. You have to apply this gate to get the unknown state, right? And this is the part where we have to do classical communication, right? Now, we're going to the next part. Here we have 0 and 1. It's the same state, but now there's a sign, the phase that we can say is different. So we can use the Z gate that is used as a phase gate to change this to plus, and that would give us the exact unknown state. Again, here we have to inform the Bob that you have to use the Z gate here, right? For the 1, 1 part, our state is like 1 and it should be 1 and 0. Sorry, my bad. This should be 0, right? So here we have to apply X gate as well and Z gate as well to get the original state. So this is what we say is a magical teleportation protocol. We started with the unknown state of Alice, and this Alice state went to the Bob, but we have to tell Bob that you have to use these measurement operators so that we know that it is not faster than light, speed of light, right? Now this is the things we're gonna do on our circuit, and we'll see that if we are able to transfer the states from Alice to Bob, right? Going towards the demo. So let's do the demo. I would be, please stop me if you guys don't understand anything, but this is the only thing we're gonna do, and I'm gonna explain every command here. So you can, when you're simulating this, that you know what is happening. The thing that I would recommend is to start with the basics. Use 0-bit and go with the commands. If you're having Hadamard gate, apply Hadamard gate and see how states flow. That's what I do as well, right? So I have a starting state, I use this, and also I use these states here for your understanding as well that what we are doing, right? So the first block explains that we are calling all the important libraries we need. What we need? Quantum circuit library, of course. We need quantum registers. We need classical registers. We need air simulator, right? And probably we need a histogram to see the probabilities amplitudes. And also we need some NP where we using the pi or stuff like this, right? So the first block is actually giving us that we are importing all the required libraries that we want to use for the teleportation protocol. Now from the top, first things first, we have to create qubits and we have to create registers. First thing, you have to initialize your qubits and initialize your registers. So we are using 3 quantum bits and 3 classical bits, right? So now 3 qubits as predefined by the Jupyter notebook, it would be in the state of 0, 0, 0, right? Now I want to explain that in these qubits, Q0 qubit is the qubit that needs to be teleported. Q1 is the qubit that belongs to Alice, and Q2 is the qubit that belongs to Bob. The same way, right? Now, first, when we were doing with the calculations, we already had the Bell state, but now we have to create a Bell state here. So now in the second demo, I showed you guys that how can you create a Bell state with the Hadamard and control NOT gate. We're gonna do the exact same here. So I'm gonna start with here. So first is what we are applying. We are applying the Hadamard gate to the index 1. So we have 0, 0, 0. In the middle one, we're gonna apply the Hadamard gate. Then we have 0, 0 plus 1 under root 2, 0, right? So now we apply the Hadamard gate on the middle qubit that we initialized, right? So that would give us 0. This 0 would be connected to this 0, 0, 1, 0 under root 2. Now if we want to get exact Bell state, we were using control NOT gate with the Alice and Bob qubits, right? So if the Alice qubit is 0, it would remain 0. If it's 1, it would be 1. So now we have a Bell state here, and we use the control NOT gate that we did in demo 2. How to create a Bell state. If you don't guys get how to create a Bell state, I wrote the comments here, and then you can refer to the last demo where I'm creating only the Bell state circuit, right? So first you can understand the Bell state circuit here, what is happening, and then you can use it in the teleportation protocol. Right, moving on. Now, we were sending an unknown state alpha 0 plus beta 1, right? That was the unknown state that belonged to Alice. But here we have to create also the unknown state because we are doing programming. We don't have to, like, we don't have predefined that we would write alpha 0, beta 1. No, we have to create that alpha 0, beta 1. For that, I am using RY gate. It is called, it rotates the qubit around y-axis. It has a certain matrix representation, and it is applying on what qubit? On 0 qubit, right? So for the 0 qubit, our predefined state was 0. Now we are applying rotational Y gate, and you would see the rotational Y gate is kind of like this, cos theta by 2. This is the matrix representation. It's also in IBM. If you guys don't know that, I would also give you a demo of this. And if we multiply it with, when we do matrix multiplications, we write 0 as what? 0, 1. Yes? So we would write 0, 1 here, and we would get cos theta by 2, 0, sin theta by 2, 1, and we are putting theta is equal to pi by 4, and by putting this, we have 0 probability of 0.924 and 1 probability of 0.147. This we know. Bob doesn't know this, right? And we want to test if we are getting these probabilities back at the Bob end or not, right? So now we have created the unknown state that belongs to Alice using a controlled Y rotation, right? All right, moving on. We have a Bell state, we have an unknown state. Next, we have kind of total state that was 3 qubits, right? I would go back to the original document where we already applied the Bell state, and the next part was to apply a controlled NOT gate, right? Here, when we had this state, right? This was the state that I explained. Now we created this state. We have that unknown state from the start, and we created a Bell state. We are on the step 1. For the step 2, we have to apply again a control NOT gate on the Alice bits, right? By applying this control NOT gate on these terms, 0 is the control bit, 0 is the target bit. It would remain 0, 0, 0. This is the control bit 0. The target bit is 1. It would remain 0, 1, 1. This is the bit where we have the control bit 1. This would become 1, 1, 0. This would become 1, 0, 1. Exactly. So this we did here, that we applied a control NOT gate. Okay. So now we are finally at the step 2. The last step was that Hadamard gate. Alice is gonna apply the Hadamard gate on her qubits, right? So here we also applying the Hadamard gate, and then we are creating a barrier just to see that we have to stop our circuit here, that we did all the operations on the Alice side. The next thing is basically to get to the measurement stuff, right? Now input 6 block explains that we are measuring these bits. In the circuit diagram, it's very clear that now this is basically where we have a barrier. Now we have all the operations on Alex side, and we want to see that if it's the state the same that we transferred in the first place, right? So we have measurement operators that are going to classical registers. Why? Because we have to tell Bob over the phone that our classical registers works with the classical bits. So we have certain conditions that if we have 1, please apply the NOT gate. If we have 0, please apply the NOT gate and the Z gate, right? To get the original state. Okay. Clear, everyone? Good. Now, what is happening? Now, here's the situation. We got to this 4 terms after applying the Hadamard gate on the Alice bits, right? And now there's a part we have to use the measurement operator to see which of the states we got. So the condition I'm using is basically if Alice classical 1 bit is 1, first bit is 1, right? Which of the 2 states has first bit 1? This state and this state. For these states, we are using X gate here and also X gate here, right? So this is the first condition where we are showing, I have also explained in the comments that states are 0, 0, 0, 1, the same state that we wrote in the other documents, right? With a certain probabilities. And the probabilities are those for the theta we used. We used theta pi by 4, which defines the alpha and beta values, right? So now, if the classical first bit is 1, then we apply the Z gate on 1, 0, right? This 0 because we want to plus here, original state was 0 plus 1. Now 1, 0, if we apply the Z gate, it would we get 0 plus 1. So again the state. And also 1, 1. But if the classical second bit is 1, then apply not. Exact. So now there's circuit explained that these are the conditions. So we have that C0 to 1, apply the Z gate, C0 to 1, apply the X gate, and then measurement operator, because I explained in the start that we have 3 bits, Q0, Q1, Q2, and Q2 is the bit that Bob has. It's the Bob part. So we are measuring the Q2 bit, right? This is the whole circuit of teleportation protocol. Now, when we made the circuit, we defined the states. What we want to do is basically to run this protocol on our simulator. So again, for that, I told you we're going to call the simulator. That would be air backend, and defining it to be QASM simulator, as in that we are using exact replica of quantum hardware, right? Then transpile is the class that belongs to QSkit, which converts our circuit into proper executable form. So we have to use this. These are some predefined rules that when we have to use quantum simulator. Then we have to explain that you have to explain our computer to explain the machine that we have to use this machine and get the result, right? So now the last two parts is basically we are explaining or displaying our results on the histogram. So first I'm going to display the results of Alice on the class. Now we're measuring the classical bits, right? We are here and we are measuring these parts. 0, 0, 0, 1, 1, 0, 1, 1, right? Now, what we see is that before we transfer anything, we had 4 terms with the equal probability, right? So first we have to see the Alex has the terms that has 1/4 probability of every term, right? Because we have 4 terms. So that would be the 24, 23, 27, and 24% probability of 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1. Right? So 4 terms, the probability is equal. The second, we are displaying the Bob part, in which we want to see that what is the probability that we receive 0 and 1, right? So 0 has probability alpha, 1 has probability beta. Now, I solved this with my hand as well, that if we use theta is equal to pi by 4, we get probability of 0.853 for 0, probability of 0.147 for 1. This is the theoretical results, but if I simulate it, I get approximately the same. This tells us that the original state that I wanted to transfer from Alice is transferred to Bob only by using control not gate, Hadamard gate, right? And some conditional things that we have to explain Bob, that you have to use X and Z gate on the measurement part, right? So now if you want to understand it better, Dr. Madhiya is going to explain this tomorrow with every gate. But now you have an idea that what is happening in teleportation protocol, and what you can do with this demo when you're gonna simulating yourself is change the alpha and beta probabilities. And then this is the program. You have to just change one line and then see did you get the unknown state that you wanted to transfer or not, right? So this demo I would be sharing in the Discord as well. I shared the first 2 demos that many of the people have joined that group. So you can simulate it, and when you guys gonna attend the class tomorrow, that you already know what is teleportation protocol, and maybe you guys can play with this, right? So any questions? All right, this means either it's very clear, either you don't get anything. This is 2 states. So I hope it's all clear. And if you have any questions, I'm available in Discord. I reply to everyone. And you can ask me anything, any gates, any demo, I will be providing you. Thank you, guys. Happy programming.
And this year,